Good afternoon, everyone. We're going to get started right away. We've got 3 presenters over our 3 hours here to do a deeper dive into envelope, mechanical, and lighting. We wanted to hopefully give everyone a both broad and deep overview of our transition from 2009 codes to 2015 and to 2018. So all of our presenters have taken a lot of care to try to kind of chart the differences between each, and are also folding in ASHRAE 90.1 as they go along. So hopefully, again, we're going to try to do as deep of a dive as we can in a 3-hour span of time. And because we have a lot of material to cover, I'm not going to take up much more of your time. So I'm going to introduce our first speaker today, Jillian Burgess, who works with the Facade Group, who will be tackling our envelope section for our first hour. Jillian?
Thanks. Hi, so I get you after lunch to talk about envelope energy code, which I'm sure is going to be thrilling for all of you. A little background, I'm a registered architect. I practice here in Philadelphia. I work for a envelope consulting firm, and many of my clients are architecture firms and building owners, and some contractors to essentially tighten up both thermal and water control issues in the whole building envelope, so from roof all the way to below grade. So even though we're called facades, we do a lot of work just focused on building envelopes from the roof all the way down to below grade, anything that keeps the building warm and dry. We practice, we've got office out in Portland, Oregon, but my practice is primarily sort of focused in the Northeast. And I've got a little bit of experience. New York City has adopted the IECC 2015 version of the codes. So we've gone through our paces a little bit with 2015 and doing energy code submissions in New York City. So I'm going to talk a little bit about my experiences there and relay some of those anecdotal stories. So for any of you who weren't here this morning, just a quick overview. We're going to be talking about 2015, IECC 2015 and its accompanying standard ASHRAE 90.1 2013, and IECC 2018 and its accompanying 90.1 2016 version. That's because the state of Pennsylvania is scheduled to adopt the 2015, 2013 versions, and the city of Philadelphia is looking to adopt, I guess is the best way to couch it, the 2018-2016 versions. And that schedule is happening in October, and there would be some grace period after that, it sounded like, till mid-spring. So projects that are probably on the boards now that maybe won't go for permit for over a year would fall under one of these 2 versions of the code. I've got some learning objectives. What we're trying to talk about is energy codes, and I'm just going to be talking about the building envelope portion of the code at the state and local levels. How the different paths to comply with those energy standards, the various implementation strategies and documentation strategies that the various jurisdictions are looking to adopt. One caveat or one note I would make. This presentation and probably the subsequent presentations are based on the national publication of the codes. The local adoption of those codes always includes some specific provisions for those jurisdictions. The Philadelphia adopted codes always have some slight language changes from the national codes, and so since we haven't seen those yet, since those are still under process, still under review, we don't know what any of those specifics are going to be yet, but these are what the national projected changes are going to be, and if you're working in other jurisdictions, these are pretty generalized standards for what the national codes are adopting. So, big picture here. The IECC compliance path, there are many methods to achieving energy code compliance. IECC governs these. Section 401.2 says your first option for energy code compliance is actually to go to standard ASHRAE 90.1. Again, if you are in a jurisdiction, the state of Pennsylvania, that adopts 2015, you could also go with ASHRAE 90.1 2013. Or if you're in the city of Philadelphia, where we potentially will adopt 2018, you could alternatively use the 90.1 2016 path. Or you can choose to follow the IECC prescriptive requirements and all of the mandatory provisions that come with it. Or option 3 is a total building performance compliance path, which is essentially an energy model based on the energy use costs, and it essentially have to be less than 85% of their design baseline building. And even with the building performance model, you still have to follow some of the mandatory provisions that I'm going to talk about in the code. I'm not going to talk about any of the energy modeling portions of it today. Those are far beyond the scope of this presentation. So I'm primarily going to talk just about the prescriptive and the mandatory requirements that are required, and then some of the trade-offs. So alternative to the IECC, you could move over and do ASHRAE 90.1, either of those two versions that I talked about. They also have a prescriptive path that you can follow. Or there's an envelope trade-off method, which many people are familiar with. That's essentially ComCheck, where you can enter in all of your various elements, and you can add roof insulation in order to have less wall insulation, and take some trade-offs in the building envelope, and it calculates sort of how those trade-offs weigh against each other. So you get an essentially overall heat loss that's the same as what the code intended heat loss would be. ASHRAE also has a similar energy cost budget energy modeling process, similar to IECC's. It's different in some ways, but I'm not an expert in those modeling methods. And then there's also a new performance rating method. Again, I'm not an energy modeler, so I can't really talk about some of those things, but my understanding is that it's simplified the energy modeling process and taken into account some better compliance options in case you wanted to follow that path. It's important to note that once you choose one of these paths for envelope or for mechanical or lighting, you have to follow it for all three divisions. So if, as an architect, you decide ASHRAE 90.1 really works a lot better for me, I got better window wall ratio values, it's really important early on in the design to talk to the mechanical and lighting engineers, because they will also have to follow it, and that comes with what you're going to learn in the next couple of hours, a lot of other prescriptive and lighting requirements that may or may not actually benefit you. And so choosing the compliance path early on in design and understanding the big implications of those paths is really, really important. And that's only done through a really close conversation and teamwork with your mechanical and lighting engineers. And so I can't reinforce enough the fact that choosing this path has a lot of big implications and really has to be done as a team. So I talked about the prescriptive path. So we've got two different codes. I'm going to try and cover both of these codes in this presentation times two different versions of them. So there's 4 sets of code that we're following. There's IECC, which the envelope portion of IECC is covered in section 402. As I go through the presentation, you're going to see at the top of the slide or somewhere on the slide where I reference different code sections. If you see section 402, that generally means it comes from IECC. Section 5 of ASHRAE 90.1 is the building envelope section. So if you see 5.5 point something, that means I'm referencing a section of code from ASHRAE. And I'll try and keep those clear, just because, like I said, the compliance paths are completely separate. You're choosing one or the other. And so they're set up in a similar method. IECC has a list of prescriptive requirements in section 402.2. It's got fenestration and insulation separated, and then at the bottom, then you'll see there's an air leakage, which is the mandatory provisions that you must follow, regardless of which path you choose in IECC. You must follow the air leakage portion of the code. Alternatively, you choose ASHRAE. You'll see section 5.4 has 3 different mandatory provisions. Again, you'll see air leakage. I'm going to spend quite a bit of time in talking about the new air leakage requirements and how that all plays out. They've also got some fenestration indoors and insulation requirements, which are a little less in depth. And then similarly, you've got a prescriptive portion of the code, which is split into the opaque and the glazed section. And they're all very detailed about all the performance factors that you'll need. And we're going to go through the prescriptive sections of both codes, compare and contrast them at the same time for both insulation and fenestration in a lot of detail. There's also a new section in ASHRAE 90.1 in the envelope section. You'll see that at the bottom, 5.9. This is only in the newer version of ASHRAE in 2016 for inspections and verifications. Although I'll go through some of it in IECC, there's an expanded section on inspections and verifications, and some of these inspections and verifications are becoming quite apparent as people are adopting codes. So we'll talk a bit about that. The thermal envelope, this actually hasn't changed, but I like to start here because it helps everybody get a big picture of what we're talking about. What is the thermal envelope? So it starts with the roofs. Any of the horizontal surfaces that are the roofs are covered under the opaque section of the prescriptive code. We've got walls. This diagram I think is really helpful. It shows we've got two sections that might be inside what we would think of as the building envelope. We've got a ventilated attic and a crawl space. But notice the dark line is inside of there. Those are not mechanically conditioned spaces, so they're considered outside the building envelope. And specifically the crawl spaces we find are often missed when architects are detailing some of the thermal envelope because you just sort of forget that the floor there, even though you think it's over part of the building, but it's actually not part of the thermal envelope. So the floor above that ventilated crawl space has to be insulated as if it were an outside space. The portion outside that architects we would call soffits is also called floors. Sometimes that gets a little bit confusing, but any horizontal surface that's sort of under your feet is called a floor, even if it's a soffit considered from the outside. And then there are a few below grade things. We've got obviously below grade walls. We've got slabs on grade, which is any slab that's less than 24 inches below grade. And I'll go into all these, all the different sections of the opaque envelope in a lot more detail. Just because I'm going first, I'm going to give you a little bit of overview. Commercial Energy Code covers everything except 1 and 2 family residential and everything but R2, R3, and R4 that's less than 3 stories in height. R2 are dwelling units where the occupants are primarily permanent in nature. R3 is 1 and 2 family dwellings, and R4 is residential care and assisted living facilities. Any of those kinds of occupancies over 3 stories in height still falls under the Commercial Energy Code. So that building on the bottom is wood frame construction. It's a 5-story residential building, falls under the Commercial Building Code. The building on the right is a condo tower, falls under the Commercial Building Code, or Commercial Energy Code. So just because something is a residential in nature doesn't mean it falls under the Residential Energy Code. Commercial Energy Code really governs many of the buildings that we're working on. IECC has a couple of new exceptions. They're just starting to recognize that not all buildings need to be insulated to quite the level of typical buildings. These are very small exceptions, low energy buildings and equipment buildings, small sort of, if you've got like an electrical utility house on your site, something, you'd have to talk to your mechanical engineers and make sure you're under the right power, watts per square foot, or energy use per square foot, and make sure it's under the area, but these buildings wouldn't necessarily need to be following the prescriptive level of insulation. They either don't need it or they need much less insulation than typical buildings. In ASHRAE, there's also several exceptions. These actually haven't changed, but I'm just going to reiterate them just to give you an overview of what's all included. Storms or replacement glazing often does not fall under the requirements of needing to be updated to code. Essentially, if you're opening up the cavity of the walls, you need to insulate it to code. But if it's already got insulation in the wall cavity, it can fall under an exemption. If you're just recovering a roof, in other words, if you're not tearing up the membrane, you do not need to re-insulate that to code. But I'll get a little bit more into when roofs kind of fall and don't fall under this, the necessity to be under the new building code, because full roof replacements, if you're tearing it up and exposing the insulation, the code specifically says that you need to insulate that roof to the new building code. So you need to usually increase the insulation in the roof assembly. Another important thing that IECC has added, and I think this is particularly important in Philadelphia where we have a lot of buildings, historic buildings, They've added an entire chapter on existing buildings. So previously there was a lot of language kind of scattered in the envelope portion of the code. It's been consolidated and expanded in Chapter 5 of the IECC. It spells out in a lot more detail the requirements for additions and alterations. It also provides an exception for historic buildings. And these are not necessarily buildings on the historic register. These are, it specifically says, the local authority having jurisdiction, that any part of the historic building that would, if complying with the new energy code, would threaten, degrade, or destroy the historic nature, does not necessarily need to be updated to the current energy code. There's going to be a lot of sort of interpretation, I think, of that code language, but they are beginning to recognize that there are going to be some exceptions to it, and they've put it specifically on the local jurisdictions to make that distinguishment. Roof replacements, like I said, still must comply with prescriptive requirements. However, roof recovering, when you're not exposing the insulation, does not necessarily need to be updated to current code. And then they've expanded. It was always a bit confusing to try and understand window wall ratios in additions and existing buildings. So they've expanded the language quite a bit to understand, to help you, give you a bunch of different alternatives to additions to existing buildings. So you can either count the addition and the existing building to meet the prescriptive version of the window wall ratio. WWR is window wall ratio. So the percentage of glazing to the percentage of the entire building envelope. You can count the addition and the existing building. You can count the addition only, or you can do a U-value average of all of the glazing. And if in some trade-offs, using a trade-off method, the addition and renovations don't increase the existing U-value, that would also be acceptable. So they've spelled out a little bit more, in a little bit more detail, how to approach existing buildings and additions to existing buildings. Like I said, there's some new administrative requirements that are spelled out in ICC. The spirit of the code hasn't really changed in any of these, but they've spelled it out in quite a bit more detail. So inspections is covered under the administrative section C104. Rather than just saying inspections are necessary, they've spelled out 6 specific inspections that are probably going to coincide with regular building code inspections, but these are specific to the energy code. These are specific energy code inspections. I pulled out the framing and roughen inspection portion of it because it describes in a lot of detail, and it's actually probably the most important one. It's the one that's going to reveal a lot of the most important parts of the envelope portion of complying with the energy code. So it's specifically telling inspectors to look for R values in cavity walls, specifically looking at fenestration products as they get installed, and checking for NFRC U value, solar heat gain, and visible transmittance numbers, proper installation. So while the spirit of this hasn't necessarily changed, the language is a little bit more extensive. And just anecdotally, what we found especially in New York City, a jurisdiction which is probably has similar resources to that of Philadelphia. And we heard this morning, actually, that Philadelphia's code, or Philadelphia L&I, they've really expanded their staff. And what we found is New York City also has. And we get building code inspectors, and then we also get separate energy code inspectors coming from the city and doing energy code inspections, and specifically looking, especially at this framing and roughen inspection, and asking very specific questions about the amount of insulation. We've had specific questions about the accounting for thermal bridging in the envelope, in the insulation numbers that we've put in the energy code compliance. So if we put a specific number for the insulation in the energy code compliance, but there are thermal bridges through it at some, in however quantity, they've asked us how we've accommodated for that in that number. Has that been thought about? So there are much more pointed questions about really the envelope and the insulation values meeting the what was put forward in the code compliance documentation. We haven't had this happen on any projects, but we've heard anecdotally from some contractors working in New York under the new energy code that stop work orders could get issued because it's part of the energy code. If you're not meeting energy code, if your insulation levels aren't the same as you put in your code compliance documentation, we've heard that they're issuing stop work orders. So that's driven a lot of our developer and contractors to really understand and actually dive in and find out, what do you mean by this installation? What do we really have to install? As they're going through the process and trying to pare down the cost of it all, they also consider the cost of a stop work order, which is incredibly expensive. So I don't know what will happen in Philadelphia. I don't know how they'll adopt it, but I do know that that's been happening in New York and driving people to be much more careful about installation. ASHRAE has always had ASHRAE added this section also. It's a little bit different than the IECC one. It again just lists specific portions of the envelope that need to get inspections, and an additional section on air barrier and air infiltration test verification. So verifying that, because the air barrier, you'll see in the mandatory requirements, is a huge portion of the mandatory energy requirements. So ASHRAE has added a separate section to verify that the air barrier continuity is being installed the way it was designed to be installed. It's interesting, the language between IECC and ASHRAE, it's a little bit different, but both of them are getting at the same thing, that we put one thing in the documentation, but implementation is really important. And so I can't tell you how Philadelphia and Pennsylvania will adopt these things in their local language, but I can say that these things are getting more detailed in the national codes, and we're seeing inspectors and code officials getting much more focused on these kinds of things. So it's important, especially for the air barriers, because that's not something you can really come back and fix all that easily. So it's important during design to have really good documentation about how the air barrier program is going to work, and follow through during construction and installation. Another change is, and this is a sort of interesting one that garners a lot of conversation, climate zones. The climate zone map has changed. IECC has not adopted the new climate zone map, but the newest version of ASHRAE 2016 has adopted a new climate zone map, and this was based on new climate data, looking at climate data from more recent years and changing trends. And approximately 10% of the counties in the country have changed climate zones. And essentially what you'll see, it's hard to see the difference between them, but if you follow the line between 4 and 5, you'll see it sort of dips towards the bottom of Pennsylvania a little bit. But if you look at the new map for 2016, you'll see it's going to start to dip a little bit higher into Pennsylvania. I'm going to zoom in on Pennsylvania in a minute just so you can see which counties have specifically changed. But the overall trend is that lines are moving upward and reflecting that temperatures are getting warmer. And they actually even added a new climate zone. It's not on this map, but it's a zone 0 reflecting even warmer temperatures. And so the climate zones affect the envelope probably the most of any of the sections. And what does that mean? It sort of means that if you're moving to a lower climate zone, well, you sort of need less insulation, except at the same time, building codes are increasing insulation. So there's some debate about how effective this is going to be, but it's an important trend to realize that we're recognizing that temperatures are getting warmer, and we have to adapt for that changing climate. So in Pennsylvania, we used to have zones 4, 5, and 6, and Zone 6 has moved completely out of Pennsylvania. Again, this is only for the ASHRAE 2016 path, so if you're in Philadelphia when we adopt the 2018 IECC in 2016, depending on which path you choose, may change which climate zone compliance you're actually using. So that's also a little bit complicated. I don't know how Pennsylvania and Philadelphia will adopt these, but I will say that the 2018 IECC, which goes along with ASHRAE 2016, they've adopted different climate. They have the IECC 2018 hasn't adopted the new climate zone map, whereas ASHRAE has. So hopefully we'll get a little bit better clarification in the local jurisdiction from that. Otherwise, depending on which compliance path you choose, IECC or ASHRAE, you may be in a slightly different climate zone. But you'll see that that whole southern part of Pennsylvania, a whole bunch of new counties have been added to Zone 4. I'm in this presentation, as I get into some of the prescriptive requirements, I'm going to be covering all four different versions of the code that we've talked about. And I'm gonna cover zones 4 and 5. If you've traveled to us from one of the zone 6 counties, I'm not gonna be covering that. But you'll see the trends and you'll see the areas of the code that are changing for 4 and 5. And so if you're looking at a project in a zone 6 climate for some of the prescriptive requirements, you can sort of extrapolate all the trends and changes. Again, all the mandatory requirements are the same for all the zones, but just to try and keep the complexity of this presentation as simple as possible, I'm only going to do zones 4 and 5 times 4 different code versions, just so you're clear. All right, so the mandatory, I've talked about this a little bit, air leakage is a mandatory requirement in both IECC and ASHRAE. These sections have gotten greatly expanded and there's a lot more detail in them. I'll talk about the differences between the two, but essentially the codes are saying your air barrier is incredibly important and air leakage is really, really important. You have 3 paths for compliance in addition to 4 mandatory requirements under IECC. And ASHRAE is actually very, very similar to this, so I'm gonna go through the IECC requirements and just know that ASHRAE is very, very similar. There's a material compliance method. You install one of the materials, and I'll go through those in a minute. Assembly and components compliance method, or whole building testing. And after I go through some of the mandatory requirements, I'll come back to these compliance path methods in a little bit more detail. So there's mandatory requirements for basically any of your big leakers, the air intakes, exhaust, stairways, shafts, things that we sort of know are big air movers must have dampers and have to be clearly closed off. There's a much more detailed requirement for loading dock weather seals. Vestibules has always been in there as a mandatory requirement, but the details of that have gotten a little bit more strict, and there's some fenestration air testing that has gotten much more stringent. There's also an exception for fuel burning appliances. This is actually a little bit complicated. So, and I've listed the section there in IECC at the top. If I've got, let's see, if I've got a mechanical room here and I've got an appliance, and my mechanical engineer tells me, oh, I need to have a louver for outside air intake for that appliance. It's just for fresh air intake to make up air for that appliance. That entire room, where that mechanical room, is now outside of your thermal envelope. That means the thermal envelope does not include that louvered room, and we're trying to get rid of that air leakage. I mean, this is sort of good practice, something that we've done for a long time. Now the code is recognizing that any room with a big outside air louver is outside the thermal envelope. That door gets gasketed and sealed. These walls, the floor and or the ceiling in that room, depending if there's conditioned space above and below it, get insulated to the full thermal value. So all of the walls, floor and ceiling that enclose that room are now considered part of the thermal envelope. It's really important for not just insulation, because now those walls get insulated, but also for the continuity of the air barrier. A few other things to note on this plan. Let's see if I've got them called out. Yep, we've got loading dock. So your loading dock weather seals, I've listed that at the bottom there, what the section of the code says. They need to be equipped with weather seals to restrict air infiltration when vehicles are parked in the doorway. So these are going to be much more stringent requirements than when we just had big roll-up doors on our loading docks. Alternatively, you could, so we've always done sort of best practice to make this part of the thermal envelope to air tighten that secondary wall. So you could make some different design decisions here to move your thermal envelope, or consider those loading dock doors as part of your thermal envelope. They need to be really tight in terms of air seal and they've got to have special weather seals for when a truck is parked in the loading dock. Another thing that I mentioned, the vestibule, you'll notice a lot of these doors don't have vestibules. Whoops. A lot of these doors don't have vestibules, but the main entry door down here does have a vestibule. Not all entry doors need vestibules. There's a bunch of exceptions in IECC. These haven't really changed that much. Let me go through this slide and then I'll get back to your question. Anything from a sleeping unit, less than 3,000 square feet, revolving doors, vehicular doors with adjacent personnel doors, which we saw up at the top in that receiving area, or doors with an air curtain. None of that's changed from the previous version. The one thing that has changed is an interesting sort of code interpretation. The code used to say that doors not intended to be used as a building entrance were not required to have a vestibule. They changed that to say to used by the public, and I think that's trying to be more inclusive of, you know, we found sort of doors like a terrace door or doors headed out to a patio that weren't necessarily a building entrance, but were used frequently by the public. And so I think this part of the code is meant to essentially say doors that are going to be used somewhat frequently, building entrance or not, if they're being used by the public, they need to have a vestibule. So I think this is getting a little bit more stringent in its requirements. Yep.
Is there an exception for the outside walls of that panel room? No insulation?
Essentially, that's outside the building envelope. So those walls don't need to be insulated. But I guess it would be a good conversation with your mechanical engineer to understand the equipment in that room. We typically would sort of do both. Depends on, I guess, sort of how you're following the code. But the important thing is that the inside, especially the air barrier continuity on the outside, must be, on the inside of those walls, has to be continuous, and a thermal envelope. Because essentially, if we're dumping a bunch of fresh air into that room all the time, it's got to be outside the thermal envelope. And the outside walls then are just outside. They're, if you go back to that original diagram I had of the ventilated crawl space or the vented attic, they're outside the thermal envelope.
There could be times of the year where that fuel burning is not occurring.
That's right. So, but usually that louver's still open. It would all depend, I guess, on how that, you know, how the system is set up. And again, that's why I say I'm not a mechanical engineer, so it's important to work with the mechanical engineer to understand how that's going to function. Yep.
Have you noticed a difference in staging or the construction process with regards to the mechanical rooms and how that moves?
Staging and construction of it?
Yeah, like, so when you want a continuous air barrier, then would you have to do the entire section of the building outside, aside from the mechanical room, and then tie?
Yeah, like these details.
Yeah.
These details become really important. Yeah, you have to think about those a little bit. There is a little bit of a constructability issue there. How do you make that look like a, you know, the aesthetics of it versus the constructability of it?
And then I'm going to continue unless you're going to have to make that entirely
A complete break.
section, right?
Yeah, those are just constructive. Yes, they are. When I get into the materials that constitute an air barrier, it's maybe not quite as stringent as it sounds. But yes, we've looked at some, in New York, we've had some very complicated details at those intersections where essentially you're separating those walls completely. Yep. Anyone else? ASHRAE also has some vestibule exceptions. They're very similar to IECC, but again, if you're following one path or the other, you've got some slightly different requirements. There are only additional requirements, the ones in bold that are new in 2016, semi-heated spaces. Actually, I didn't mention this. ASHRAE has a third conditioning category for semi-heated. It's always been in the code. It has different envelope requirements. I'm also not going to talk about those envelope requirements because it adds a whole nother layer of complexity, and semi-heated are less common conditions. So I'm just trying to cover as much of the common conditions as possible. They also put these entrances from parking garages as an exception to the vestibules, and that's something that's pretty interesting because we always get into this debate about, a parking garage below a building, does that need a vestibule as a building entrance? And so ASHRAE has recognized that as an exception. IECC has not. Often we see things that get adopted in one version of the code, get adopted in the other in the next one or two subsequent revisions. So I would expect some, in 5 or 10 years, some better language on parking garage entries. Was there a question? Fenestration air leakage requirements in IECC have gotten much more strict. It went from just saying curtain wall and storefront and swinging door requirements to this whole list in Table 402.5.2. Just to give you an idea of the increase in the stringency of this, curtain wall and storefront in 2009 IECC were listed at 0.3 CFM per square foot. Curtain wall and storefront are now listed, let's see, right here, 0.06. So we went from 0.3 to 0.06 CFM per square foot. We're getting a lot tighter. So you've got to look at the products that you're specifying and figure out if they meet this. Swinging doors went from 1 CFM per square foot to 0.2. And then we've got a whole bunch more categories of various products. You need to have that AMA or NFRC stamp on the product, part of the U value, part of the solar heat gain requirements by code to be able to install that product in the field. Manufacturers should have these tests and should be able to provide this. If you have a product that doesn't meet these air leakage rates, you can still do whole building testing of your air barrier, but that's, as most of you probably can assume, a much more involved process. So if for some reason you would like to really use this one type of curtain wall, it doesn't have the NFRC test, or the NFRC test doesn't meet that 0.06 CFM per square foot, you still have the option to get a really good installation and do a whole building air test. And I'll show some examples of that in a minute. The details of the air barrier construction plan haven't changed. We're looking at the same things we're kind of always talking about in air barriers: junctions, changes in plane, ducts and plenums, joints, transition in materials. So that's unchanged. They're basically looking for continuous continuous air barrier around the entire envelope. They've got some interesting language in there about how joints and sealants must resist negative pressure. So they're getting more specific and more stringent requirements for that air barrier, and just trying to tighten up the envelope. Then, like I said, there's 3 methods for compliance. So after you've done all that prescriptive stuff, you've got all your weather seals, you've got your fenestration products selected. You then have 3 different other methods of complying with the mandatory requirement for air barrier compliance. One is materials testing, and they list all these materials. They're very, very similar lists in ASHRAE and in IECC. These are also fairly unchanged from previous versions of the code. You have assemblies, which are very similar to different materials, block with a couple of layers of sealer on it and things like that. These are not very stringent requirements when we're talking about super tight buildings. And then, like I said, you've got the whole building testing method of compliance. And these are whole building air tests that essentially pressurize the building and test how much air leakage you have. And what you'll see there are some thermal images that were taken during a whole building air test. So it was actually, this one was done fairly recently. So it was done on a cold day. The building was heated up. The building was then pressurized, and anytime you see those sort of the arrows pointing at the bright white and orange spots, that's hot air leaking out of the building. And we found them leaking at really typical spots that the code is actually already calling out: joints around windows, transitions between materials, recessed light fixtures is another really big one. And the code specifically says it actually calls out recessed light fixtures now and says you need to have certified light fixtures that meet air barrier requirements, and you've got to make sure it's installed correctly. So these are things that are going to start to become more strict requirements as part of the air barrier plan. ASHRAE has the similar whole building air testing requirements, same air leakage rate requirement, 0.4 CFM per square foot. They go into additional detail about building size. Bigger buildings don't have to do a whole building air test, which is incredibly complicated to do. They can just test the specific areas of the building. So if you've got a high rise, you got to test the top floor, you got to test the building entrance floor, and then about 25% of the other floors. So you can get a representative area. Then they go into a little bit more detail and tell you what you have to do if you don't meet that air barrier test. IECC doesn't tell you what you have to do if you fail the test. ASHRAE gives you a little bit more leeway if you're between 0.4 and 0.6 CFM per square foot. You can do some diagnostic evaluation, which is those therm images I showed you a couple minutes ago, perform some investigations, and write a report saying how you've remediated those things. So you've got a little bit of leeway in the code for those things. So those are the mandatory provisions of the code. Oh, sorry, there's one more. Forgot about the insulation. Insulation is getting a little bit more detailed. It's not really as in depth as air barriers are. IECC 2015 and the ASHRAE versions just tell you if you've got multiple layers of insulation that you've got to stagger the joints It's pretty good practice. Most people do this already. IECC 2018 just clarifies that and says you have to have 2 layers of insulation on the roof. You can no longer just do a single layer of insulation on your roof. Must be 2 layers and they must be staggered. So we'll see in a minute as I get into the prescriptive requirements for roofs. We're increasing the insulation on the roofs anyway, and so now you just have to do 2 layers and stagger the joints. And that's just, studies have shown pretty conclusively that staggering the joints prevents airflow and reduces some thermal loss between the joints if you've got them aligned. So now I'm going to try and go through all of the prescriptive requirements. I'm going to try and go through them as fast as I can to try and keep us on time. I'm going to go through them as fast as I can, so let me know if you have questions as we go. These slides are all pretty much set up the same way. We've got, this is our current code requirements in the state of Pennsylvania, ASHRAE 2007 and IECC 2009. The second column is ASHRAE 2013 and 2015, what Pennsylvania is looking to adopt. And the third column is 2016 ASHRAE and 2018 IECC, what Philadelphia is looking to adopt. So, like I said, there's layers upon layers of the complexity of this. I'm trying to go through both zone 4 and 5, but you'll start to see trends across all of these. So roofs are getting a big upgrade. We're going to go from R20 CI, continuous insulation across our roofs, to R30 everywhere in Pennsylvania. So we're beefing up the roofs because that's shown to have a huge return on investment. Insulating your roofs is always a good investment. And the other one is that ASHRAE, both ASHRAE codes have updated the attic, the sort of insulation between joists below the sheathing, from an R38 to an R49. I'll show you what those things mean in a minute. There's always the U value alternative. So in the prescriptive path, you can follow these prescriptive numbers. You can put R30 CI up there. If for whatever reason you don't want to follow that path, there's always a U value equivalent. So you can figure out the U value of your roof assembly and follow these. You'll notice the numbers in bold are the ones that have changed from the previous code versions. The R value changes and the U value changes are meant to go hand in hand. So when an R value increases from 20 to 30, the U value is also going to decrease to represent the same percentage change. So what does this mean? We went from R20 CI, which was 4 inches, to R30 CI, which is 6 inches. For most commercial construction, this isn't a big deal. It might change some of your parapet and flashing details. Maybe your dunnage and things have to get a little bit higher, but for the most part in new construction on flat roofs, this is not that big of a change. I mentioned that ASHRAE 2016, that ASHRAE changed to R49 bats. That's going to change framing and insulation requirements below sheathing quite a bit. And like I said, once we see some changes start to happen in one version of the code, we often see that start to happen in subsequent versions in the other code. So this is potentially something we're going to start to see happen. And yes, there are R49 bats on the market. It's just, changes in sort of how you're going to frame out that roof assembly. So these are by no means the only way to achieve a roof. I'm just trying to give you some examples to sort of give you a better picture of what the numbers mean in reality. I mentioned we do a lot of roof recovery projects and re-roofing projects. Existing buildings are particularly challenged with this code upgrade. You can see if this door sill had R20 or even R10, this is an old building here in Philadelphia, upgrading the roof insulation thickness here at this door sill is going to cause a lot of problems. Similarly, we end up with a lot of flashing and parapet details on old buildings. So there's always, that's why I show the U value alternative. There's always an option to do a mix of above and below roof, depending on your design considerations and in terms of what's happening in the rest of that building. There's also trade-off methods available that I'll talk about later, but essentially you could you could double up the insulation in one area of your roof in order to have less insulation in another area of the roof, and do some trade-offs that way. But essentially the roof insulation requirements, new construction are fairly straightforward. It's the existing buildings where we're getting a little bit more challenged, I would say. Above grade walls, this is one of the parts of the prescriptive code that have changed less than other parts of the code. For me personally, the disappointing one is you'll see metal frame buildings. What we build most of our commercial construction out of, metal studs. with bat insulation and a little bit of CI remains completely unchanged in Zone 4. And only in ASHRAE 2013 and 2016 do we see in Zone 5 some increase in that, but really still a fairly nominal increase in that construction. And so that's one that I think is disappointing, but still unchanged. Mass walls similarly are unchanged in their insulation values. But we'll see wood frame construction, and this is really probably the biggest design change, is that wood frame construction changes in both zones. And particularly here in Zone 4, we go from R13 bats, probably in a 2x4 stud wall, to requiring either R20 in a 2x6 stud wall or bats with continuous insulation. So your wood frame construction in both zones is actually going to change pretty significantly. Again, those U values increasing to match the R values. So just to give you a sort of graphic example of what this is going to mean, what we've been building for wood, this is just wood frame construction. We've got wood frame construction. We used to have, what we've been building in Pennsylvania and Philadelphia, R13 and 2x4 construction. We've got to go to either 2x4 construction with continuous insulation, 1 or 2, about an inch on the outside, or you've got to go to 2x6 wood studs on the inside with bigger bats. So that'll have some implication for some of the smaller scale wood frame construction. Similarly, Zone 5's got some upgrades. Zone 5's always required some continuous insulation. They've actually included now that you could do 2x6 with bats in the stud cavity, which you really always could do with a U value alternative. They've just made it a little bit more prescriptive and spelled it out in a little bit more detail for you. And then ASHRAE is actually increasing that CI a little bit more. So we're seeing ASHRAE get a little bit ahead of IECC, and we may see in subsequent versions of IECC in the next 5 or 10 years, some of these CI numbers catch up. Below grade walls and slabs on grade. These numbers are significantly changing, and these are again kind of similar to roofs, a little bit less painful in the design process, but really important to keep in mind, especially in constructability and construction sequencing. In Zone 4, we used to have no requirements for anything below grade. Now we've got our 7.5 CI across the board, now matching what Zone 5 was previously doing. And all of our slabs on grade now are required to have insulation at the perimeter for 24 inches below grade. And I'll show you some of the diagrams from IECC to explain what these numbers mean, what R15 for 24 inches below grade really means. But essentially, in most of Pennsylvania, you're going to need R15 for 24 inches below grade on your unheated slabs on grade. And all of your below grade walls need continuous insulation. C factors and U factors. So for the most part, we talk about U factors in building envelope. Below grade walls and slabs on grade don't have U factors. They have C factors and F factors. Essentially what that's doing is taking into account the three-dimensional heat transfer with ground contact and understanding the heat capacity of ground. And they're based on like 10 or 15 years, 20 years, I forget, of academic research in the heat transfer of these assemblies, especially mass walls and ground transfer. There's tons of tables in ASHRAE to be able to look up. I've got a 12-inch foundation wall with 2 inches of insulation. What is my F factor? So there's pretty extensive tables to find out what those things are. Otherwise, you can just use a prescriptive version. It's pretty straightforward. Yep.
Back on the above grade walls, the wood framing.
Yep.
Does the IEC allow you to mix bat insulation and continuous exterior insulation?
Yes.
To meet the minimum requirement?
Yep, and remember there's prescriptive requirements. The U values are also prescriptive, so if you mix and match, you can still always figure out your U value equivalent. And similar to all the other things, there are tables in ASHRAE that will help you figure that out, so you can look up wood frame construction at 16 on center and find your bats and figure out what the U value equivalent of that assembly would be. So yes, there's always mixing and matching allowed. But, and you'll specifically see it here, they list it out. That's what these numbers mean. Sorry, I'm going too fast through it. R13 means bats, and then the CI number is the continuous insulation after it, whereas the R20 is just bats. So these are two different, oops, I'm sorry, I'm running ASHRAE. These are the IECC bat and CI numbers that are prescribed by the code. Yes, I'm happy to take questions as I go. Stop me. I'm trying to go fast through this. There are a lot. These are the diagrams for what has to happen. So I said that R15 for 24 inches below grade. These are the diagrams so you can have your insulation either inboard or outboard of the foundation wall. And it's 24 inches below that exterior grade line, not below the first floor line. And it can go down to so if you've got a 36-inch footing, you don't necessarily have to go all the way down. Similarly, you could do 24 inches horizontal at the perimeter of your slab on grade as long as the insulation turns up at that foundation wall, similar to that detail right there. And below grade walls, this image is sort of flipped from the last one, what's interior, not exterior. These are the exterior, but essentially it's saying the IECC allows you to put that insulation on the inboard or outboard portion as long as it's continuous. But they do specifically say provide some continuity with below grade and above grade. So it's not always feasible, but you've got to think about that thermal bridge if you've got discontinuity in your insulation and what happens in the foundation to above grade wall condition. So some design considerations there. Floors, like I said, IECC and ASHRAE consider floors same as soffits. I don't know, for me it's a strange language thing, but anyway, horizontal surfaces that are soffits and floors, anything that's over an unconditioned space. The only change here is that mass floors just increase in insulation a little bit. So we go from, and only if you're following the ASHRAE version. If you're following IECC, there's essentially no change in the continuous insulation. ASHRAE is up to the continuous insulation below mass floors, just a little bit to 14.6 CI. Other joists insulation hasn't changed, R30 insulation inside metal or wood joists. And the corresponding U values to go with those. Fenestration, so glazing and fenestration has increased significantly and gotten a lot more detailed. I'll try and go through these as quickly as I can and explain as much as I can. Stop me if you have any questions. The biggest change that people are finding is that IECC has gone from a maximum window wall ratio from 40% to 30%. Now there's some exceptions, you can still do 40%, but prescriptive, if you're just going to follow the simple prescriptive portion of the code, you are now limited to 30% window wall ratio, which architects are struggling to deal with, I think, in some cases. U values for framing has all gotten greatly improved, and they've changed a little bit of the language. So instead of curtain wall and other framing for metal frame construction, we've got just fixed fenestration and operable. I think it clarifies things a little bit. But again, we've gone from a U value of 0.5 to anywhere from 0.4 to 0.38 in zone 4. And in zone 5, we've gone to down to a 0.38 for fixed fenestration. They recognize that operable fenestration with bigger frame sizes can have a little bit higher U value. But still now wood frames, or wood and vinyl frames and your non-metal frames in zone 5 have gone from a 0.4 down to 0.32, 0.38, 0.30, depending on which version of the code you're following. So these performance factors are getting much tighter, and you've got to be much more careful in selecting your products and talk to the product manufacturers about NFRC testing. Make sure you've got the NFRC stamp on there, because that NFRC testing and requirement is required by code. It always was, it still is, but code inspectors are now looking for those certifications much more carefully to make sure that these U values correspond to what's installed in the field. So I mentioned that IECC requirement down to 30% window wall ratio, which is causing some serious design struggles or challenges. You are allowed up to a 40% window wall ratio with some daylight responsive controls. And I'm hoping our Lutron representative will talk a little bit more about some of those daylight responsive controls. These are essentially, you've got to allow more daylight into the space. You need no more than 50% of the conditioned floor area within a daylight zone in buildings less than 2 stories above grade, no less than 25% of the net floor area within daylight zone, buildings more than 3 stories above grade, and daylight responsive controls. So there's going to be some cost implications if you want to follow prescriptive to go up to 40% window wall ratio. Alternatively, there are some trade-offs you can make in CommCheck, but this is going to get you really have to carefully choose your path if you're going to follow, if you're not paying for energy modeling early on in the design process, to choose which prescriptive path you want to follow. And remember that all of the architectural implications and the envelope considerations have serious mechanical and daylighting and lighting energy implications that may or may not be good. So choosing which path early on is really important, and working closely with your engineers. Yep.
When you say choose your path, if you wanted to do a building with more windows, then what would be a good choice?
So if you want more than, so if you're looking at up to 40%, you could choose ASHRAE. So if ASHRAE still allows up to 40% window wall ratio. But understand all of the, there's a whole bunch of things I've already gone through, and there's a whole bunch more things I'm going to go through. So, as you've probably watched this presentation, you've already said, I want to do ASHRAE seems easier. Now hold on, IECC seems easier. Now ASHRAE seems easier. You're going to go back and forth a bunch of times. There's a lot of exceptions that I haven't even listed that I'm trying to go quickly through. It's a complicated decision, and they're getting a little bit more complicated. So, being told I got 5 minutes. So there's some solar heat gain has gotten more complicated. Again, this is choosing your path. ASHRAE still allows 0.4 in 2013 for solar heat gain coefficient. 2016, they're getting a little bit more stringent. ASHRAE's got some more things to do with, so both codes have implemented orientation-specific solar heat gain language. IECC's made it simple. On the north facade, you can just have a higher solar heat gain coefficient by code. And they list different solar heat gain coefficients depending on your projection factor. Projection factor essentially is what kind of shade, do you have external shading? And so you've got a bunch of different, you can, essentially the more shade you have in the north facade, you can have a higher solar heat gain coefficient, higher visible transmittance, which is what architects are often looking for. ASHRAE's got a complicated metric and calculation for allowing higher solar heat gain coefficients. I've listed the equations here. I'm not going to get into them too much. This is the simplified. What it basically means is you've got a building that's oriented this way, you've got a little more leeway in your solar heat gain. You've got a building oriented this way, you have less leeway in your solar heat gain coefficient specifications. And just to sort of illustrate why solar heat gain is so important, I don't know how well these renderings came out, but you can sort of see all three of these are really high performing glass. They're all down at a U.25 for the glass type. So these are really good low E coatings, but you go from a solar heat gain of 0.34, which is now meeting the code prescriptively, but you only get a visible transmittance of 50%. All the way up as you increase to like a really high solar heat gain percentage, you can get up to a 78% visible transmittance. So visible transmittance and solar heat gain are going to go hand in hand, and those are the design implications of those decisions. Doors are getting a lot more stringent. So we went, entrance doors essentially go from 0.85 down to a 0.77 across both climate zones. Similarly, opaque doors are getting more stringent. What does that mean for designers? This door, which we see a lot of entrance doors, are a frameless single glazed door. That's like a U value of 0.9. That's not going to make it anymore. So if you're choosing prescriptive or you're choosing this, is that a decision you want to make? Can you find a product that meets these more stringent U value requirements as you go? Skylights are also really, really tightening up, and this is just showing you how bad skylights are for energy. I'm sure your mechanical engineers always say that. So skylights are going from essentially in half from 0.6 to 0.5 in IECC, but the U value of 1 to 0.5 in ASHRAE. So we're getting down to a 0.5 factor for skylights, also only 3% of your roof area. That remains relatively unchanged also, so limited skylights. Right, back to our compliance path. So those are all the prescriptive, mandatory and prescriptive requirements that are listed in both compliance paths. And as you can see, they can be incredibly complicated and incredibly restrictive at the same time. So choosing one or the other, like I said, you got to have a conversation. But there's also probably a lot of things, that maximum window wall ratio of 30% is going to give a lot of building owners and designers a lot of angst. So there are other compliance paths available in the envelope section. You can do the most popular one, the one everyone really knows, is the building envelope trade-off method using ComCheck. ComCheck is pretty good about updating. They don't have IECC 2018 released yet, but they're working on it, and they often do. They've never done a Philadelphia-specific one, but many local jurisdictions like New York City has their own version of CommCheck, and so you can get very specific about your climate zone. You choose your location. IECC also has a envelope trade-off section. You don't necessarily have to use CommCheck. You can use what they call the components performance alternative. This is a little bit different than using CommCheck, and you may want to use this for one reason or another. They provide this spreadsheet in IECC. Essentially what you're doing is you're adding up the U value of all your walls, roofs, and floors, your slab on grade and below grade, F, C, and F factors. And then you're doing a calculation of essentially the excess glazing area. I want to increase my glazing area, so how much extra heat loss am I going to get in there? And they're essentially trying to quantify all of that, and how much potential excess skylight area. And so you can do these kinds of trade-offs using this spreadsheet and not necessarily going to a building energy model to understand, to be able to still be code compliant, but it potentially means adding a lot of wall and roof insulation to be able to accommodate slightly more glazing. So that's one method of compliance. You can also use CommCheck for IECC compliance as long as it's acceptable in your jurisdiction. And the Building Energy Codes program has a really good website. You can go on there. It's also helpful to find out what your current code is. But they also will say if CommCheck is approved for IECC and or ASHRAE use in your jurisdiction. Often they are in some of these bigger, in any of these jurisdictions, but it's important to know whether you can. Almost all of them, I've never come across a jurisdiction that doesn't include CommCheck, but important to know that it isn't necessarily always approved. So it's good to look on there. And so CommCheck. So if you don't want to follow any of these, all of the prescriptive requirements I just listed, you can use different trade-offs. You can increase your roof insulation to decrease your wall insulation. So it does allow various trade-offs. In ASHRAE, you get full range of trade-offs, and it's actually backed by now an energy modeling program, so it's not just running straight up numerical calculations, but it's actually running a little bit more complex energy model in the background. IECC is still a little bit more simple, and it does have one important caveat in 2015 and 2018 that has come up and then is very important to realize. So if you're going to use CommCheck, ASHRAE allows you full trade-off. You can have worse windows and increase your wall insulation. In the IECC, there's a part of the code that says individual fenestration projects from different fenestration product categories cannot be combined in calculating an area U value. And if you go into CommCheck, it'll pull up and you're in the IECC portion, it'll pull up this fenestration requirements. And essentially that means all of your fixed fenestration has to average out to a maximum U value of 0.38. They have to exceed that, even though you're doing a trade-off. So you could have a bunch of 0.4 windows as long as you have a bunch of other 0.35 windows and they average out to below 0.38. But you can't trade off worse doors for better windows. All of your doors still have to meet that maximum U value of 0.7 averaged out. So each one of those 4 fenestration categories still has to average out to that maximum U value. Now you can get better. You can do a really high-performing curtain wall and reduce your roof insulation. So you get better credits, but you're still hitting the maximum for each category. And that's one that has been a little bit tricky because previously and in ASHRAE versions, you are allowed to trade off worse windows for better insulation. But here, you still have to hit the maximum U values for each category. So I think I didn't go too far over. Hopefully I didn't go too fast through some of that. But it's a lot to try and cover. So it's a lot, so I'm going to try and summarize it as best I can. Inspections and implementation are getting stricter for envelope compliance. We're seeing these air barrier and U value inspections. Like I said, I had a code inspector ask, how did you accommodate the thermal bridging in this insulation and when you put in for your code compliance? And we had to, in the documentation, show him where we downgraded that continuous insulation from its rated R value to what we downgraded for the thermal bridging for some wall bracing. The climate zone map is changing in ASHRAE 2016 only, but stay tuned and check what happens when Pennsylvania and Philadelphia adopt to find out what happens to various counties, especially surrounding Pennsylvania, in the climate zones. The air leakage requirements, much more stringent, isolating those outdoor air intakes, loading dock weather seals, tighter vestibule requirements and fenestration requirements. The prescriptive requirements are increasing, specifically roof insulation, wood frame walls. Slab on grade and below grade wall insulation is increasing. Much more stringent U factors and solar heat gain coefficients. And the window wall ratio in IECC is another really big design implication for envelopes. And the more stringent door and skylight U factors. Specifically, the entrance doors, I think, has been what we've found in going through design and code compliance reviews. The entrance doors, small percentage, but not being able to trade that off with other things limits the products if you're doing a prescriptive code compliance. And then the trade-off methods, that new code compliant, the new component performance alternative in IECC, and the underperforming windows, meeting that maximum U factor for the windows for each separate fenestration section is a new challenge. So hopefully, yep.
Do you think the changes in the climate zones from what they were with the zone 6 existing in Pennsylvania and zone 5, zone 4
Yep.
situation, would that change the system assembly thought process of certain architects, or do you think?
Well, so it's interesting because as we're downgrading, we're still increasing insulation requirements. So overall, we're still increasing insulation, other than those metal frame walls. So it's changing a little bit. I think we do have to be aware and look at humidity in conjunction with all of this to understand what kind of air barrier and water barrier we need when we're doing dew point analysis, because those are some of the things that are going to change. And that's not really prescribed in the code. It's just careful design consideration.
So you think as long as we're increasing the amount of insulation, then there's not going to be any change in regards to where the dew points are, any concern regarding?
No, I would say you have to, each design is so specific. Because dew point is also so much a factor of what's going on inside the building. Right. A residential building with spikes of RH at various points of the day is very different from an office building, which is very different from, a building where there may be pumping humidity in for whatever reason. So dew point calculations are incredibly building and site specific. That's why code doesn't really address it, because it's such a specific thing. You can't really prescriptively define that. So. You all sleep? Everyone glazed over with the numbers?
We could technically figure that out, what the best assembly was, big, and that exact calculation.
Oh yeah, we do that all the time. For every project, we figure out what the perm rating on air barrier should be, depending on what the specific requirements are of that project. And there are pretty regional design considerations that, there's regional acceptable wall assemblies that are pretty tried and true, and that's not changing so drastically. So
I'll let Susanna load that up, but also I did a great job of introducing this afternoon session. Hi everyone, I'm Katie Bartolotta. I'm the Policy and Program Manager with Green Building United, one of 3 organizations that's hosting this afternoon. We're here along with AIA Philadelphia and ULI Philadelphia. And I also want to thank, while I'm up here and remembering to do my job, to thank AIA Pennsylvania also for providing videography for this event, because this will help us reach a much larger audience. And so I'll let Susanna get working here while I give some other announcements. So I just want to let everyone know too, slides will be shared afterwards, because again, we are cramming a ton of information into a very small amount of time. And again, I thank our presenters for covering all of the possibilities that we are likely to see here between Pennsylvania and Philadelphia. Again, not an easy feat. So we will share all of this after the fact, along with everyone's contact information. If, a couple hours down the line you think, oh, I have another question that I wish I'd asked, in our very short Q&As. So I will turn it over to Susanna. We'll have an hour. Ready?
And go. Okay, hi. Those of you who saw me this morning, there's going to be very little repetition, but to introduce myself, I'm Susanna Hansen. Like she said, I'm with Trane. I've been working with ASHRAE 90.1 for a really long time, and so I have a little bit of the history of why things are the way they are, and sometimes I can weave that into my presentation, sometimes I can't. But if you have questions, feel free to ask them. If it gets too onerous to answer them all in the course, we might hold them to the end, but we'll see how it goes. Okay, so I'm Chapter 6 of 90.1, or what is it, 403 in IECC, which is the, generally speaking, people refer to it as the HVAC section. It's really mechanical equipment. And then there's usually something on surface water heating that has been fairly neglected, unfortunately, in my opinion, in both standards. I'm not going to be talking about that either. So just exclusively, really, the mechanical section, and then I'm also going to touch a little bit about the energy cost budget method, but only for very briefly. So like Jillian really teed up well, there's basically a couple of different paths. There's actually more paths now in the 2016 version of 90.1 than there ever have been, and we're going to go through that a little bit. Those of you who didn't get two of these, they're in the back. These are the newsletters I wrote that summarize the changes in 2010 and also in 2013. There is a 2016 newsletter in development. You can subscribe to have it delivered to your inbox when it's available. So I just wanted to encourage you on that. There is some blank pages in there if you want to take notes, and it's deliberate. Okay, enough of that. Okay, so there's some mandatory provisions that basically mandatory means you can't get out of it with an energy model, if you want to think about it that way. There's also a simplified approach, which no one really ever talks about, but it's for those small buildings, 25,000 square feet and smaller, 2 stories or fewer, and that use packaged equipment. So those types of buildings don't have to go through quite as much rigor within the energy codes. So I wanted to bring up this climate map again. We talked a little bit about it this morning, quite a bit about it, and then Jillian just brought it up. I wanted to make sure that everybody was aware of how this works. So whenever we talk in the mechanical section, unlike envelope, we have subclimates. So within climate zones 2, 3, 4, 5, and 6, there's moist and dry designations. And then in 3, 4, 5, and 6, there's also marine designations. So whenever I say 5A or 4A, that means I'm in coldness 5, moisture high. If I were in 5B, that would be mostly cold or temperate, they would call it, and dry. Okay, so it's not necessarily in order of stringency or coldness. It's cold plus moisture plus precipitation, if you want to think about the marine climates that way. Okay, so that's enough of that. I'm going to skip right over the equipment efficiency updates just because it's pretty dry and the equipment manufacturers have pretty much handled it for you. If they didn't do it themselves, the DOE did it for us through their rulemakings. So this is pretty much already baked in. I encourage you, if you want to look at those in more depth, you can look through the slides when you get them or in the newsletters that are also available to take with. So generally speaking, though, the only change that we're doing to equipment efficiencies other than increasing the stringencies where we can is we're trying to increase the scope. So as new classes of product come on the market, we're looking for a test procedure to be defined, a certification program, hopefully, and then a level to be set by some form of either industry involvement or in some cases, ASHRAE will do it themselves. So that's pretty much the deal. So VRF, for example, came into the standard in the 2010 version with an effective date of 2012. DOAS equipment came into the ASHRAE 2016 version. I did not see a corresponding entry into the IECC in 2018 for DOAS equipment. So those are just two examples, but the other big examples are refrigeration equipment. So freezers, reach-in, as well as walk-in refrigeration equipment is now covered under the scope of both IECC and 90.1. So that's the kind of examples that I'm going to do there. So I'm going to skip over to the prescriptive changes just because we don't have a whole lot of time. So in the prescriptive section for Chapter 6, and I'm going to have some deviations between 90.1 and IECC that I'm going to point out, and you'll see those called out. So here's just a list of the prescriptions that I felt were worthy of discussing or at least listing. for my sanity, I usually put the addendum letters so I can go look up the backstory when I need them. So, and the only times that you can see those backstories and the justification is during the public review. So those of you who haven't yet subscribed to the standards actions from 90.1, if you do that, you'll get a notification when there's a public review open. And during the public review, I highly encourage you to download those documents because you won't find them published with their backstory and their documentation again from ASHRAE. So that's my tip of the day. So let's see, I'm not going to go through all of these. I'm going to skip over a few, and I'm just going to go through in order. I've hid the ones that I thought were maybe less interesting for you. But generally speaking, these prescriptions are going to affect the price and cost of the equipment more almost than some of the efficiency tables. And some of the efficiency requirements are kind of falling out of some of these other requirements that we're going to talk about, such as what we used to call single zone VAV requirements. We're seeing the entry of more variable speed fans, in some cases variable speed compressors, and all of those have an impact on efficiency. And so some of the efficiency tables reflect that and some of them don't. But that's what this prescription list kind of shows. So there was this new concept called fan efficiency grade invented. There's actually a replacement sort of in negotiations right now. It was sort of an attempt to help people select better fans for the application. It was sort of successful. There's been some deficiencies in it, and so that's why we're back at the drawing board a little bit on fan efficiency. So there's that. Cooling towers had some turn down requirements, and each of these has supplemental slides, so I'm going to wait to talk about those, but here's the list. You can see, for example, though, that exhaust air energy recovery is prescriptive in 90.1, however, it's mandatory in IECC. And there are exceptions, and one of them is a pretty big loophole. I'm not sure what we're going to do about that, but other than that, you see these door switch interlocks that are in 90.1 but not in IECC. So just as Jillian said, there's sort of some reasons why you might prefer the 90.1 path to the IECC path. There's also reasons why you might prefer the IECC path to the 90.1 path. And it gets even more complicated now once you leave the envelope sphere and you have to talk about your mechanical equipment as well. In the 2016-2018, here's a quick summary where I have the little asterisks. The single asterisk is when I didn't find a coordinating 2018 requirement, although I didn't see myself use them. I meant to put one on. So for example, I didn't see chilled water reset, although it might be there. Multiple zone ventilation optimization is not in IECC. Not sure about a couple of the other ones. The 2018 IECC is pretty new. I just got a red line, and it's a little bit difficult to figure out what changed because they sort of struck entire sections and they replaced them entirely. So it's hard to tell what was already there but just written in a different section before. So any apologies in advance if I misspeak a little bit. You'll have to do a little bit more homework once you leave here. So I'm going to talk a little bit about some of these. The divergence would be in the waterside economizer. So I'm going to talk about that in the aggregation slide a little bit later. Oh, I had builds, that's why. Sorry about that. Makes sense. Okay, so here's that fan efficiency grade. This is trying to attack fans larger than 5 horsepower. Below 5 horsepower, there is no requirement because FEG really falls away below 5 horsepower. They also, the biggest change to design practices to select within 15% of your peak efficiency. So in systems where you have a really wide swing in pressure that the fan has to operate against, that provision can be actually very difficult to meet in some cases. So it seems to be creating some winners and losers in terms of fan choices, and that's why we're so keen to get a replacement for that. But in addition to the FEG or the fan efficiency grade, we have this thing called the system fan power limit. And the system fan power limit is in horsepower per CFM. And the horsepower per CFM is for the whole system. So if you've got a fan that's got 300 feet of ductwork, it's going to have maybe a little bit harder time meeting versus a fan system that only has, 75 feet of ductwork on the critical run. So designing systems well is certainly going to be something that system fan power limit is going to constrain you on and require you to do. But I will point out, it had been assumed, and I'm not sure where we fell on this, that where the fan is already included in the efficiency of the equipment. Some people say that that's not a system that falls under this category, this system fan power limits. Some people do. There's a little bit of an argument going on about what counts, but I think we finally did settle that packaged equipment does still have to meet the system fan power limits. For cooling towers, the big change here is that we're wanting you to run them a certain way. So when you have multiple cells, we want you to run the maximum number of cells at the same fan speed. This gives you effectively a larger surface area, which makes your cooling tower more effective. We want to also make you have some good flow turn down. If you have the ability to turn a cooling tower cell down to 50% of its flow on the water side, that means you can flow one chiller over 2 towers, and that makes your tower more effective as well. So those kind of provisions are going to change the way we operate and maybe even select and design our cooling towers. This was a big change that's causing a lot, I think, of the energy savings, and that's all of the developments that have happened within the fractional horsepower motor space. You've probably heard of ECM motors, electronically commutated motors. You also will hear them called brushless DC motors. Basically, these motors, there's varying degrees of flexibility in them and cost, of course, but generally speaking, when they're applied, they have less efficiency losses at part load. You can tune them for the speed that you're actually needing. Some of them are still run in a multi-speed environment. Some of them are more variable speed. But in any case, down to 1/12 horsepower, we're looking for ECM motors. So series fan-powered VAV boxes, for example, unit ventilators, fan coil systems. Those types of little motors are basically going to be more efficient motors now. If you did still have a belt-driven fan for whatever reason, I can't imagine, but if you still do on a new product, you're going to have to do some shift adjustments there. Boilers have better turndown requirements. You can do that either by a combination of better burners that have more controllability, or by using staged boilers that have, in the collective, the same turndown effect. And that is the same. And so on these slides, I'm going to point out with these little blue splatters, if you want to call them that, whether they're the same or different. And sometimes when it's red, it's worse, and sometimes when it's blue, it's the same, well, you'll see. Okay, so this one was called the single zone VAV expansion. It's not truly single zone VAV because it really talks about how we do our compressor staging and how we do our fan speed control. So in the original incarnation of single zone VAV, we basically said that we wanted you to be able to turn down your fan speed, especially during economizer mode. So the second to last bullet here, if you have an economizer mode, we want you to have at least 2 fan speeds during that mode. And then depending on how you control the system, we want you to be able to have lower fan speed. So the idea is we want better part load humidity control, which means less cycling, which means less overcooling and discomfort, which can lead to energy waste as well. So all of these things were sort of made, this I think originated in California in their Title 24 process. And this was sort of a reaction to manufacturers sort of saying, hold on, we've got this packaged equipment. It already has an efficiency requirement. You don't need to tell us what kind of equipment's to put inside of that equipment. California said, yeah, that's not good enough. So they came up with some of these requirements that effectively changed the design, particularly of unitary packaged equipment, to make it a lot more efficient. And so you have to give credit where it's due to California sometimes, sadly. But the effect of these changes that are really inside the equipment have been far-ranging and really energy-saving. So here's the table for that, and they're all effective dates are all in the past. So this has to do with what happens when you come out of economizer mode. And economizer mode is, of course, when you bring enough outdoor air in to offset the cooling load without turning the compressor on. There's an integrated mode where you do as much cooling as you can with outdoor air, and then you can kick on the compressor for the last little bit. Well, what happens in unitary packaged equipment is that if the compressor's too big and it kicks on, the controls of the unit can what's called dither the damper, and they'll close the outdoor air damper to sort of false load the compressor to keep it from cycling or to keep it from overcooling the discharge air. And so that became another way that economizers failed, because the actuators on the dampers were constantly open and closing, but it also led to energy waste. And so that sort of drove this change to have more compressor stages. If you have more compressor stages, then when you bring on that first stage, it's smaller and it's much less likely to cause this sort of control interaction that's meant to protect the equipment and also the comfort of the occupants.
If you have a space that has critical humidity requirements, 45 saturated, that bring humidity down versus, coming off 53 saturated or something like that. Is there an exception for that?
So the way that dehumidification limits work, this will actually help with dehumidification now.
No, but we may have a space where we actually need higher humidity. We have some process, farm space.
Not that I know of. I don't know that there's a specific exception that says you don't have to do this if your humidity requirements are such that you want it to be higher. I think you have better control of humidity altogether with this than you would have had without it. This doesn't say that you have to cool to a specific dew point leaving your unit. It just talks about how small the compressors need to be, or how many of them there need to be, how many stages.
But say your outside air damper must stay open.
Oh, okay, so that's an economizer requirement. So, yeah, we're going to talk about that.
If I need to maintain space
Yep.
humidity
Yep.
55 saturated.
You're right.
I need to fit in an exception.
So that's an exception for the economizer, but it's not an exception for this requirement. However, this requirement sort of did, in some versions of the standard, get sort of underneath the economizer section because it really was driven by that. It's since been moved out of that section in some of the standards, so it's a little bit independent of that requirement. So you might not have to have an economizer, but you might still need to have multiple stages of compression. It's hard to say. I probably could look that up. Any other questions on this before I move on? Okay. So one of the things that the standard 90.1 and I believe IECC is almost the same as this, requires that you have some sort of method of eliminating simultaneous heating and cooling. 90.1 went a little bit further and said that, well, we don't want you to have humidifiers in the airstream that are unintentionally adding heat to something that you just cooled. And so there's some limits on doing almost really accidental or incidental simultaneous heating and cooling at the central unit. So that's what that is there. And so this one is the last bullet, is what affects you, the one with the high dew point discharge requirement, which is you're not allowed to use an airside economizer if your space has to be humidified to above 35 degree dew point. And so if that's the case, then you would have to use a water economizer rather than an air economizer. You don't get out of it entirely, you just aren't forced to use, not like you were anyway, but you're not allowed to use an air economizer, because we know that would increase your humidification load if you were doing active humidification. Let's see, here's this system fan power limits. It's an equation. I will bring your attention to this little A term. This A term is the adjustment number. It's essentially, and it's on the next slide, a summation of the pressure drop times the CFM divided by the constant there that converts the units. So A is effectively an addition to your brake horsepower limit, and you only get this A term if you're using the brake horsepower path. So there's two paths to use here, either the nameplate horsepower of the motor or the brake horsepower of the motor. And engineers in the room, brake horsepower is essentially a calculated number that you'll get from the equipment manufacturer, or in some cases you'll have to calculate it if you're doing a built-up system, for example. But that's where that A term comes from. And so there's a table that I don't have in here that's going to give you different adjustments depending on what you've got, whether it's Deeper filters, like for example MERV 13 filters, and better would get a pressure drop adjustment. If you have other things that are in the airstream, such as energy recovery devices, you'll get some additional pressure allowances because of those devices either are required for the application potentially or save energy in different ways. So that's the system fan power limitation. The thing that's different between 90.1 and IECC is that you can trade system fan power for something else in 90.1, but you cannot in IECC. So mandatory in IECC, you're basically in the soup if you can't meet it. The things that are different in the IECC 2018 and the 90.1 2013 is we started to reduce the amount of credits that you get. So you don't get sound attenuation credits unless you really need a really quiet space. You don't get credits for fully ducted systems unless you really, oh, that's in the new version. This one has to do with cooling or heating coils. So just makeup air systems without any conditioning don't get a full credit because they don't have pressure drop through the coils. I mentioned this morning for those of you who were here. One of the things that really is a way that buildings, envelopes, and the mechanical equipment need to work better is on the interface between operable windows and doors and the air conditioning system. The switches for operable windows are more expensive to implement, and so while it might have started out as a full fenestration, whether it's a window or a door, it now has to, well, I guess doors aren't always fenestration. The glass ones are fenestration, but otherwise it doesn't matter. Okay, so it ended up being that we just have the door switches, and there are exceptions with automatic closing devices, unconditioned spaces, loading docks, etc. You can change those, but this is another place where 90.1 and IECC deviate. I don't believe that this is in IECC. Unless it's in a different chapter and I didn't find it, which could be. So exhaust air energy recovery is a little different between 90.1 and IECC. The table's the same. IECC is mandatory, 90.1 is prescriptive. So one of them you can trade, the other one you cannot trade. And so the way that this table works, it's a little complicated. Let's look at the upper table. So in this upper table, depending on what climate zone you're in, so let's do 5 and 4A, because that's where we are. Depending on the CFM, total CFM of the unit, if we have a large unit, 26,000 CFM, and we're 10% to 20% outdoor air, we need to have an energy recovery ventilation system. And the way that requirements work is you basically have to do total energy recovery. You can't just do sensible energy recovery unless you're in potentially like Tucson or some really dry climate. Potentially you only have to do sensible. But in most of the areas of the country, you're having to do total energy recovery because we're looking at the enthalpy change between the two airstreams. And there's some nuance there, but as you get into colder climates and higher percentage of outdoor air, you're more likely to be triggered to go into energy recovery ventilation. So that's the way that this table's working.
All right, so the architect's question is, does this mean like every building just about requires energy recovery now?
Not really. It has to do with the size of the unit. So if one of the ways that someone might get around it is they put a lot of small units on, which is an unfortunate unintended consequence because it is system type, system size related. Any system that has a dedicated outdoor air unit should have to have energy recovery ventilation on it. Because it has more than 80% outdoor air. So anything over 0, it's actually changed to 140 because it's really hard to go down to 0 in little residential spaces. But basically any system that's a dedicated outdoor air system should have energy recovery on it. Having said that, I know we only ship about 30% of our units with that. So there's a lot of people that are finding loopholes, unfortunately. And so what we try to do is limit the numbers of loopholes. And so as you look at the developments that are happening in the standards, it's usually an attempt to either go more stringent or reduce loopholes. Because that is a really good thing for the middle of the country, because in 4 and 5 and 3, you have heating and cooling savings And it's of course really important in the really cold climates too because of the dominance of the heating. It still pays off in the hot climates too because of the downsizing of the cooling equipment that you can achieve by doing energy recovery ventilation. So that's why climate zone 1A and 2A actually have some requirements too. This was a cost justified table. So you can probably argue until you're blue in the face, but this is the table. And it's the same regardless of which version of the standard you're in, 90.1 or IECC. Another thing that changed and really affected the controllers that we use on VAV boxes. This is basically forcing us to do a little bit better control at the VAV boxes. We're going to need to use discharge air temperature sensors in order to accomplish this little control right here. We can't do it just with the air valve position. We have to also look at temperature coming off the unit to affect either the SCR electric heating coil or the hydronic heating valve in that unit. So this has all been done by the manufacturers. Well, most of the manufacturers, I believe, have done this in their VAV controllers. And the goal of this was to reduce the amount of reheat that happens during the cooling mode. And the other reason why we did it is we wanted to be able to limit the heating temperature that we deliver off the unit because that affects the amount of short circuiting that we have, which affects the amount of wasted energy that we've made trying to heat a space from above, which doesn't always work that great. So there's a couple of different reasons for this requirement. This one is in IECC now. I had this no IECC, but that was in the 2015. I believe I did see it in the 2018 IECC. Okay, so fan pressure optimization has been in the standard since like 2007. It's been in there for forever. The only change now is that there's some people who are really concerned that rogue, quote unquote, rogue zones would affect the control, because what we were asking people to do is use the critical zone to drive the fan speed directly. So you would pull all the zones and you'd find out which is the most open zone, and if it were all the way open, you would increase the fan speed. If the worst one was partially closed, then we would decrease the fan speed. There was concern that there was always going to be one zone that was never happy. It was at the president's office who had it turned down to 50, or some conference room that was hosting a meeting and somebody modified the set points and never put them back, or something like that. So the new provision is that you have to identify where these rogue zones are and be able to eliminate them from the algorithm. The other option is that you can no longer set your DP, your differential pressure set point in your ductwork, so that its set point is any higher than 1.2. So that's the other option now, is either you put this little P where this purple P is, that's where the differential pressure pickup for the duct is, and the engineering standard was sort of like 2/3 of the way down the duct on the critical run. The critical run moves around all the time, but having it down the ductwork somewhere is sort of trying to reflect the average pressure at the boxes that are downstream of it. And so the idea is if you can place that so that its set point is no higher than 1.2, then you're far enough down the duct that you're able to get a pretty good representation of the zone's pressure requirements. So there's two ways to do it. One of them is this 1.2 maximum set point. The other one is to have a method within your control system of identifying rogue zones and removing them from the optimization logic. That's too long-winded. I gotta get moved on to that one. Too much on that. Okay, so pump pressure optimization is very similar to fan pressure optimization. This one, we want you to look at the critical zone to set your valve, the critical valve position to set your pump speed. So we want you to stop pumping too much pressure into your valves. Number one, it wastes energy, and number two, it decreases the life and the controllability of your valves. If your valves aren't very controllable, then your spaces aren't comfortable. If your spaces aren't comfortable, then you're going to be wasting energy or having tenants move out. And so there's a lot of good reasons why not to pump too much pressure. So we look at this, and this threshold is coming down. It used to be larger systems. It's coming down to smaller and smaller systems. And generally people accomplish this with a VFD on the pump. If you want to do it with pump pressure reset based on critical valve, you have to have data about the valve position, so it requires some DDC controls in your space. We'll talk about that a little bit more in a bit. Okay, so economizers is the biggest change that'll probably be coming up in your conversations with your HVAC contractors. It used to be that economizers were not required until you got to Climate Zone 5A. So 1A through 4A were exempt in the version of the code you're in now. Going forward, you're going to be required to have economizers. You can choose either air or water economizers. I will say that we justified the costs based on an office building application and an airside economizer. It's probably the rosiest application that we could have probably done, and if I had a time machine, I'd probably go back and do it differently. There are exceptions, there are trade-offs. It is prescriptive in 90.1. I believe it is also prescriptive in IECC, so you could trade this off using energy modeling. But they are different, and I'm going to talk about how they're different. So the way that economizers are different in IECC is you have this aggregation clause. Now this is the clause that came into IECC before it came into ASHRAE, which is sort of a rare thing. It was proposed to both at the same time because the proponent was really serious about getting it in there. However, 90.1 sort of rejected it in its form that was sent to IECC and rewrote it differently and did more analysis. So there's a divergence, and I'm not sure that that divergence is ever going to close. So this is where areas where it's slightly different. IECC 2015, so all of Pennsylvania will have this aggregation clause in it. It's slightly different in 2018, but not that much for IECC. So the premise is, okay, I have this exception right now from having to have an economizer if my individual terminal unit, my fan plus coil, were less than 54,000 BTUs, which is about 4.5 tons. I didn't have to have economizers regardless of how many of those things I had. So the premise is, let's imagine an office building with fan coils in it. It's a high-rise hotel that's got a good fan coil system in it. Everybody likes chilled water in the hotels. They get the big bucks per room night there. If there's a whole hotel full of these little fan coil units, why don't they have to have some sort of a waterside economizer cycle? And so the aggregation clause was meant to go after those systems that could have a water economizer but had been exempted before. So that's where this is. The threshold for basically the chiller size, if you're in water cooled, it's 60 tons in 4A, it's 110 tons in 5A. Air cooled has a slightly higher threshold. That's because it's not as cost effective on air cooled systems to put that in. And whenever possible, we leave the designer's discretion on how to meet the codes and design energy efficient buildings. In the 2015 version of IECC, you only have an efficiency trade-off in 2B, 3B, and 4B, so that's nowhere near here. That's like North Texas and maybe parts of New Mexico. You're not going to see that here. However, in the 2018 version, there is 2A, 3A, and 4A also in that table. So in the southeast Pennsylvania areas that are in 4A, or in Maryland, or New York City, for example, once they follow IECC 2018, you can get an efficiency trade-off based on the part load metric. So if you're in a unitary piece of equipment, it would be IEER, and if it's 20% better than the minimum table, then you can get out of the economizer. There are exceptions. There's 10. It's on the next slide. One of them I already mentioned, which is the dew point control that usually affects hospitals and patient care areas, but it could be other applications. You mentioned something like a process, I think. Condenser heat recovery, if you're doing that, it sort of works at cross purposes with economizers, because the time when you're shedding the cooling load is the time when you wanted to recover the energy from the condenser. So you can't usually have both of those in the same system at the same time. So there's a crosswise exemption there. I already mentioned the energy efficiency thing. There's a better efficiency trade-off table in 90.1. Here are the exceptions. The one that seems to be used the most is number 1, but that's going away in IECC because of the aggregation clause. That's pretty much it. Computer rooms have a little bit different exception, and it's not in the IECC version. So here's the efficiency trade-off table that's in 90.1, and it's the same table in the 2013 and the 2016 versions. So if you were in climate zone 4 and you were able to get 42% better on the part load metric versus the table value, then you can use this to get out of having to have an economizer. And this is a group here that's really concerned about energy conservation, and I just wanted to point out that as you look at existing buildings, and there's some new clauses that force existing buildings to go into things like economizers that maybe they didn't have before, there might be some constraints why you can't possibly do it. And so we wanted to give you a good option for saving energy that was at least mathematically equivalent to the effect of the economizer. So we ran models and we figured out how much energy the economizer would save and coordinated that with the amount of energy that a more efficient piece of equipment would save, and where they cross is where we put these values. And so that's how this table was derived. We wanted to give people options instead of just not doing it all, an air economizer or a water economizer. You can instead use one of these. And it doesn't work in the really cold climates. Like I can't imagine ever finding something 59%, 64% more efficient. It's really difficult. But in the climate 4, I think you're pretty close. 49% in 5A, you might get pretty close depending on the class of equipment that you're looking at. Again, this is not just for unitary. This works for chillers. This works for other pieces of equipment that are more applied than we used to have as well. Any questions on this? You're like falling asleep. Let's try to keep it lively. All right. So the other thing that IECC did a little bit earlier than 90.1 is fault detection. When we have economizers that are working on our outdoor air intakes, we collectively as an industry surveyed a bunch of units, and we found economizers were either broken or disabled way too often, or they were economizing when they shouldn't be, or not economizing when they should have been. So fault detection came out of that significant emotional event about how useful our economizers really were. And so fault detection has been embedded into the controllers on unitary packaged equipment, primarily driven by California, but now it's countrywide through 90.1 and also through IECC. I'm not even on the right slide. Oh, that's the second bullet. Okay. All right, well, anyway, I'm going to talk about something else in a minute. Fault detection is coming up. Next slide. Okay, so the 2018 version of IECC has these little 2A, 3A, and 4A included with their dry climate counterparts. So the 20% improvement, this one allows you to do it on full load or part load. So depending on the type of equipment, you may find it easier to meet one or the other of those. So either full load, EER, or IPLB. So that was something I learned last night, and that's why it's on this special jump stick now. Okay, fault detection. If we're looking at, fault detection's image is at the bottom, but we're talking still about that economizer exceptions. So in IECC, this aggregation clause exempts still the DX coils. So if you have a direct expansion coil, such as one in like a packaged terminal air conditioner, or maybe in a water source heat pump, or a VRF system, then this aggregation clause doesn't apply to you. And that's, to be honest, one of the reasons why 90.1 didn't like the way it was written, because it seemed to pick winners and losers. And we wanted to find a more comprehensive way to incorporate all terminal products, not just some of the terminal products. Some progress has been made towards that end, but we haven't finished that process yet. So the economizer fault detection is on the next slide here. What we're talking about trying to figure out is when our sensors have gone bad or are broken or are reading improper numbers. So we want those sensors permanently installed. We don't want them only there for commissioning and then removed. So we're looking for some good accuracy over that range in the quality of the sensors that we're installing. So this is a design criteria for the sensor selection. We want to indicate status. If you go up to the unit and you notice that it tells you some way, either through blinking lights or through a real language, what is it called? words, essentially, words. If it tells you in words that something's broken, you're able to call for service to have them go out and fix it. A lot of these are on the BACnet interface. You can actually have them dialed up and maybe fix things from your internet connection, or you might have to roll a truck out to replace a sensor. So the status that we have to have as a minimum is whether or not it's available, whether or not it's enabled, and then if there's other limit cycles that are active or not, and what those values are. So there's other requirements too that has to do with this manual operation. You have to be able to override the unit controls to do some testing and validation, having those fault reports accessible, and then here are some of the faults that have to be enunciated. So I have a unit that I built for the show, the ASHRAE show, in 2013, 15, I built a unit that I could break one of the sensors and show the enunciation happening on the unit controller. So you can sort of see how that's working. And this is a really good, I think, improvement to our suite of packaged products. The next thing I want to talk about a little bit is pump control. In the past, like I sort of mentioned, that we had this 10 horsepower, 5 horsepower sort of VFD requirement. There was a movement underway by some of the really progressive energy conservation wings, if you want to call them, or factions, that wanted to reduce them from 5 horsepower to like 2 horsepower. And we were sort of like, time out. Let's go back and analyze this. And so what happened on the analysis is we found that our existing requirement of 5 horsepower was maybe a little bit too not pay back, that it didn't pay back as much as it needed to pay for it. And so some of these actually relaxed and some of them went more stringent. So in the more cooling dominated climates, we're having variable speed pumps more often than we would in the opposite of what I just said. Oh, hot water pumps and chill water pumps. So this is a really complicated table the way I've written it here, isn't it? So chilled water pumps, hot water pumps, and then the threshold. So the thresholds stay the same. We're moving around the climate zone designators. So I'm going to point with my little pointer here. Chilled water pumps in the hot climates have a lower, like I said, lower threshold, and the colder hot water climates have a lower threshold than the cooling dominated climates, essentially. So this is much more complicated than it was before, but it is cost justified now, and we're confident in it, whereas we wouldn't have been if we had just cranked the numbers down. Any questions? I really botched that, didn't I? Sorry about that. This other thing happened in 90.1. It did not happen that I saw in IECC. Sometimes there's a delay, and sometimes there's a rejection of our argument within the IECC code process. I'm not sure which one happened in this particular instance. I somehow won the lottery and don't have to go to the IECC hearings. But it's hard to say. So one of these, because I mentioned ASHRAE 90.1 is a design standard, so what we're trying to give you is not necessarily how to operate your buildings, but how to design your buildings so that they operate, they have a chance anyway, if you do it right, of operating very efficiently. And so one of the requirements that came up in the last code cycle that I was involved in at ASHRAE was this chilled water coil selection requirement. This came out of a desire by some progressive folks to at least require 6-row cooling coils. That isn't exactly how codes get written, because we're not trying to prescribe a solution, we're trying to prescribe a performance level. So in order to get the pump savings that we want to get without having to prescribe a specific type of coil, we instead specified a range for that coil. So a delta T, or a flow rate, essentially, minimum delta T, essentially of 15. Now that doesn't necessarily mean that the chiller has to be a 15-degree delta T chiller. It just means that your coil has to be capable of doing 15. And oh, by the way, it also has to get to a 57-degree return water temperature. So essentially the minimum would be 4257 then for the coil selection. And then ideally, you would get a chiller that could do the same conditions so that you could take full advantage of the flow reduction in order to offset any potential air side pressure drop of the deeper, potentially coil. Now, I will say that in some of our analysis, we looked at the trade-off between coil depth and fan energy consumption, and we discovered that if you looked at some of the latest guidance on coil selections, you can remove the airside pressure drop penalty by spacing out your fins per foot, even on a deeper coil. There's other things that you can do to the circuiting of your coil to make them a little bit more effective as well, to help you get to that 57 without necessarily going to a deeper coil, because we don't really care how you got there. We just want you to be able to have the pump energy savings of that delta T. A little bit complicated. Any questions on that one? Seeing none, I'm going to move on. This close to last one, I'm getting to the end, which I'm sure everybody will be happy about, including me. So replacement equipment. I think I mentioned this morning that we had this sort of kerfuffle with the Department of Energy where they were saying that equipment manufacturers were being a little bit, we were accused of being a little bit facile about how we thought we were doing in terms of increasing the stringency and the efficiency of our products, because we were all still maintaining the lower efficiency products because there were jurisdictions that were not yet following the more recent energy codes, Pennsylvania. But you aren't the worst. There's plenty of other states that are worse than you, but we were maintaining this class of product that was not really up to snuff, and one of the reasons is because of states that weren't adopting the more recent versions. But the other reason is because there's a clause that I didn't even know was in there that said if you did a like-for-like replacement, meaning I just plucked this rooftop unit on and I put a new one on, the only thing I actually had to do was meet the new efficiency of that particular product. I didn't have to do economizers, I didn't have to do controls interlocks, I didn't have to do the time schedule thing, I didn't have to do a whole bunch of other mandatory things that are within the rest of the building that interfaces with that equipment. And that, like I said, was a shock to me, because here I was thinking that we were doing really well, and it turns out not so well. So what we did in the most recent code cycle at 90.1 is we looked at the things that we were saying that you could potentially do even in a like-for-like replacement scenario. So we went through 2 or 3 rounds of public reviews on this. It was not popular. I'm going to have to tell you, it was a bit contentious. But what we ended up with is these, I don't know, what is that, 10, 8, 9, whatever, requirements that you still have to meet even if it's a like-for-like replacement. Starting in 2016, similar requirement also in the 2018 IECC. So you're not going to be able to do just a constant volume unit, even if you're in a constant volume application, meaning you don't have diffusers. We want you to have a variable speed fan on that anyway, although I can't imagine there are still constant volume, no reheat, but I suppose there are still those systems. Anyway, so we had some requirements that got added, even for like replacements. So this is really going to make a big difference, I think, on existing buildings, which have fewer options on upgrading some of their other systems. Putting better HVAC equipment in there and upgrading their capabilities is it's a win for the energy conservation quest. So a little bit about the energy cost budget, because there's been some changes to that you may find useful, especially for a couple of the people that aren't in the room anymore. No, he's still here. Okay, we're going to talk about your little table from before. So the energy cost budget has been in there for a really long time. This is in 90.1 what's called Chapter 11. You also might be confusing it sometimes, like a lot of people do, with Appendix G, which is the modeling rules for LEED and above code programs. So the energy cost budget basically said, okay, here's the system that you get to use for this particular type of building. And you don't get to sort of, you have to pick the same system in Chapter 11 versus your proposed. So it's a little bit different rules. And so if you found a prescriptive requirement that you didn't like or you couldn't do, you could always use, if you could show that your energy cost was at least as good, if not better, than the baseline or the budget in the case of Chapter 11. So this is something that's always been in there. No one really likes saying, hey, if you don't like it, you can always do an energy model. That's certainly not a very compelling argument, but it has been used, and it has been used successfully by our practitioners as well. So there's a new path, and so in the old days, it used to be that if you're doing a LEED project, you had to do an Appendix G model, which is taking a specific system for your type of building versus your proposed. And if those were a certain amount better, you could get LEED points or some sort of an incentive program with your state, for example. Well, that caused an additional modeling burden if you're trying to use that model for your energy code compliance. And so instead, and there were some other reasons that we didn't really like it too, and I'm going to talk about that on the next slide. But the new thing is to be able to use Appendix G, the Performance Cost Indicator, or PCI, Performance Cost Index, to identify whether or not you meet the standard, as well as let it be used for your above code program. So the things that we did to make Appendix G useful as a code compliance path is we switched to a fixed baseline. And one of the challenges that our states have had is they want to prescribe a certain percent better than the minimum code, rather than continuing to update their code. They want to just keep cranking up on the performance requirements. And it isn't just states. It could be LEED, it could be Green Globes, it could be some other above code program wanted to have a fixed baseline. The other value of fixed baseline is the energy modeling software can have the baseline not changing, so we can have better compliance tools that don't take as much time and effort and money to update every 3 years. So we also noticed that some of our buildings had, I'm almost done, had a easier time meeting the percent better than other buildings, and in some climates, and I showed that this morning, some climates had a bigger advantage than other climates. And so there's a table by building type and climate zone. I'm going to show you that. So there's an index and a target, and depending on which version of 90.1 you're in, you will just see this table will just keep changing through the years. So the first table just came out this time. I imagine the next table that comes out will be probably 7%, 5 to 7% more stringent than the current table, depending on the building type and climate zone. Anyway, so there you read probably by the time I finished talking. Okay, so this performance cost index is basically saying you've got your baseline, plus there's a portion of your building that's unregulated versus regulated. I also talked about that this morning. Regulated loads are things that are actually in the standard. Unregulated loads are things that are not within the purview of our standards. So printers, copy machines, projectors, coffee makers, ice machines, those types of things are not part of what we regulate within the energy codes, at least these ones. Maybe Energy Star does, but we don't. So you go through that little exercise and you come out with a number that's essentially a fraction of the performance cost index. So energy cost is the basis that we use for our energy codes. And the reason for that is because we don't want to encourage fuel switching. I don't know, for those of you, probably some of you were maybe aware of what was going on in the 90s, which was what was called the utility wars. And so the gas people and the electric people were going like cats and dogs, trying to affect the changes that they wanted. And it caused this 10-year gap between the 89 version and the 99 version, among other things. So we went to cost as a way to eliminate sort of this fuel switching shortcut that people might have taken towards energy BTU savings rather than source energy. So site source and fuel switching and all that, all wrapped up into it. But if you look at this number, this is a cost index. So for example, if you're in 4A, which you are, and you're in an office, this one says that you, if you use this path, would have to get about 42% better than the 2004 baseline if you were in office. If you were a school, you would have to get 51% better than the 2004 baseline. And so all the modeling rules got codified back to 2004 if you're going to use this method. It's sort of a little bit of a trial balloon. We don't know for sure how well this is going to be received, but we decided to put it in there to see if it stuck. So if you like it, please let us know. I don't know if anybody will, but some people might. So in summary, our envelopes may be getting less expensive, but not because we're still going better, just not as much more insulation as we might have otherwise. I didn't talk about lighting yet. That's coming up next. Controls is important. We're getting closer and closer to requiring commissioning. We're looking at things like fault detection and diagnostics are going to be followed on by acceptance testing in some form or the other. If I had my crystal ball out today, that's what I would say. Coordination between the systems. It's kind of implied in some ways, but otherwise it's not implied. Sometimes it's very overt that we're going to do there. I didn't talk about central plant monitoring, but large chiller plants have to be monitored now and submetered. Fault detection you can read as well as I can. Lots of different things, and so I feel for you guys. You're going from 2007 all the way up to, in some cases, 2018, we think. That's a huge step change. It's more than a step change. It's a quantum leap in some respects that you're going to have to get up to speed pretty quickly. I don't envy the code official and his team that were in here earlier and maybe still here at their job that they have to get acquainted with all the various new provisions. I'm going to open it up for questions, maybe just a couple. No? Oh, you confused the heck out of you guys. I love it. All right, that's it. That's all I got. So bring Katie back up.
All right, everyone. Last presentation of the day. We're going to move into our lighting section here, and we have Michael Giovanni with us, who is the Manager of Sustainability and Energy Standards with Lutron. Michael is also a board member of Green Building United and on our Policy and Advocacy Committee, so he's been following this pretty closely. So in addition to having the technical expertise, he's also been following everything legislatively that's led up to this. So we're really happy to have him today. And I'll turn it over to Michael now.
Great.
Thanks.
Can you guys hear me in the back if I talk this loud? Okay. A little louder? All right, because I don't like standing behind the podium. So. Okay, let's roll. 48%. 48% is the projected percent increase in world energy consumption by 2040. All right, so just think about that number. We already live in an energy-starved world today, and if we don't do something about it, it's just going to get worse in the future. 66%. That's the percentage of energy we waste each year in the country. Okay? So think about that. We actually waste more energy every year than we use. Okay? 5%. We are less than 5% of the world's population, but we use about 20% of its energy. Okay? So I'm Michael Giovanni. I'm Lutron's Energy Code expert. And I'm going to be talking to you today about the importance of building energy codes and how they can help meet some of our energy issues, and in particular, how lighting controls in particular, how do they meet some of the requirements in the latest energy codes. The topic is called Codes and Controls, how lighting controls help meet the Commercial Building Energy Code requirements in ASHRAE 90.1 2016, IECC 2018, and California's Title 24 2016. Okay? We are going to be focused on IECC because that's the Pennsylvania-based code. So these are the learning objectives. First, we're going to look at U.S. Department of Energy data, and you'll be able to describe the importance of energy conservation in buildings and how light control significantly helps. Okay? And then we're going to look at some lighting control strategies, and you'll be able to explain how light control saves energy in commercial buildings. And the meat of the presentation is the third objective, and that's we're going to look at the latest Commercial Building Energy Code requirements for lighting, and you'll be able to determine how light controls help meet those requirements. And then lastly, we'll look at a real-world example of how they use lighting controls to meet and actually exceed energy codes. Okay, I want to start by showing you this graph from the Energy Information Administration. This shows you back in 2003, lighting actually used by far the most electricity in commercial buildings. Okay? Now, with the latest data that was released last year, lighting has gone down a lot as far as electricity use in commercial buildings, all right? But it's still the number 2 user of electricity in commercial buildings behind other. So what's other, right? Other, according to the Department of Energy, Energy Information Administration, is mostly process loads, fans and motors, and some miscellaneous electrical loads, so potentially some plug loads there too. So lighting is still a low-hanging fruit as far as energy savings, even though it's gone down over time. I also want to point out a couple of things on this graph. Computers have gone up significantly, and so has office equipment, all right? So we have to keep an eye on those. But this is the problem that we see. There's a lot of wasted lighting energy in commercial buildings. Most buildings are way over illuminated. Okay? Most buildings were designed based on old IES, or Illuminating Engineering Society, recommended light levels. Okay? And those recommended light levels have gone down over time. Secondly, most buildings don't take into account the available daylight, the free sunlight to illuminate a space. Okay? Thirdly, most spaces in these buildings, even though they're vacant during normal operating hours, leave the lights on. Okay? So you get a lot of spaces like this, like you see in this picture here. You know, it's daylit, it's vacant, yet the lights are left full on, wasting energy, wasting money. I like this quote from Steven Selkowitz from Lawrence Berkeley Labs. He said, "Most buildings don't deliver the right amount of light where and when it's needed. Lighting is often set at a worst case level, which is usually higher than desired." So the solution is light control, and these are the primary ways that light control saves energy in commercial buildings. We all know, number one, lighting control conserves energy by reducing the operating hours of the lighting. Okay? In other words, switching lights off, saves energy. We know that, right? Secondly, when the lights are on, light control saves energy by reducing the wattage of the lighting, or the power of the lighting, while the lights are on. Okay? In other words, dimming lights saves energy. In fact, the graph you see here is a LED dimming curve, all right? And it's basically linear. The lower the light level, the lower the energy usage. Okay? And it's the same looking graph for fluorescent, incandescent, halogen, basically the same looking graph. Okay? Thirdly, light control saves energy by reducing cooling load. Okay? Why do you guys think that is? Any ideas? Why does light control reduce cooling load? That's right. So when you reduce lighting in the space, there's less heat coming into the space, therefore you don't need to cool the space as much. The rule of thumb is for every 3 watts you save on lighting load, you save about 1 watt in cooling load. That varies by a lot of factors. Geography is a very important factor there, and the more south you are in the country, the bigger that savings is, and the more cooling they use. And lastly, light control saves energy by maximizing the effective use of sunlight in the space. So when we talk about light control, we are not just talking about controlling the electric lights, but we're also talking about managing the sunlight that's coming in and taking advantage of the sunlight to illuminate the space, and also making sure that the sunlight's not a large source of solar heat gain. This is a quote from the director of green buildings for the GSA, and I like this quote. because we talk a lot about energy savings and energy efficiency, but we have to remember that there's people in these buildings. And Kevin basically said 0 energy buildings that provide 0 comfort or 0 productivity increases to the occupants are of 0 value. All right? So that's the beauty of light control, is not only does it save energy in buildings, it also improves the comfort and productivity in the spaces. Let's look at some key light control strategies for commercial buildings. There's scheduling. This is where you schedule lights, say at night, to sweep off after operating hours. Okay, that's typically done with what they call a time switch or a time clock. Okay, technically it's really a time switch, or an astronomical time switch. So it doesn't just necessarily do it by time of day, but can do it by astronomical events like sunrise and sunset. Occupancy and vacancy sensing. This is where you have sensors in rooms, and they know when the space is vacant or empty, and lights will automatically turn off when the space is empty. Okay? And there is a difference between occupancy sensing and vacancy sensing. And basically, occupancy sensing is automatic on, automatic off. Okay? And vacancy sensors or vacancy sensing is manual on, automatic off. So a person actually has to push a button, flip a switch to turn the lights on, but the lights will automatically turn off when the room is vacant. There's multi-level lighting or dimming, basically giving occupants additional light levels other than just full on and full off. Okay? And daylight harvesting. This is taking advantage of windows and skylights, taking advantage of the daylight coming into the space, and using that light to illuminate the space and reducing electric light when there's enough daylight in the space. As far as which of these are common, this is an order of commonality in commercial buildings. About 20% of commercial buildings do scheduling, right, which is surprisingly low. And then just under that is occupancy sensing. This is based on the same data from the energy information, the CBEX data. And then we get much lower, to less than 10% for dimming and daylight harvesting. Okay, some more advanced light control strategies. There's high-end trim or tuning, and this is where you set a maximum light level in the space, okay, lower than the true full-on light level, all right? The nice thing about this strategy is the first 25% of lights going from true 100% down by 25% isn't even detectable by the human eye, yet you save about 25% in energy, okay? Personal light control. This is giving occupants the ability to control their lighting in their individual workspace. So change the light levels based on the specific tasks they're handling in their individual work area. Controllable window shades. So we're talking also about helping control the daylight that's coming in, all right, and taking advantage of that free sunlight, but also making sure that's not a large source of solar heat gain and glare by using controllable window shades. Demand response or demand responsive lighting. It's actually a requirement in California's energy code, not in IECC or ASHRAE. But that's basically reducing lighting levels when you get a signal from your utility to shed load, a demand response signal. And then there's plug load control. All right, this is automatically turning off appliances like plugged-in lights, okay, and other appliances to conserve energy. Remember, I showed you that graph, and I showed you computers, and office equipment was growing fast. It's the fastest growing. So this is an important area to keep an eye out for. Okay, let's look at a visual example of these light control strategies in action. If we lighted an office building to 1 watt per square foot, it would use 8.76 kilowatt hours a square foot of lighting energy in a year. Okay, we just lighted up to that level. Then we throw in the scheduling and we sweep the lights off during the non-operating hours. Now you're down to about 5 kilowatt hours per square foot in a year. You do occupant sensing. You're turning lights off when the spaces are empty. Now you're down to about 4 kWh per square foot of lighting power in a year. You do the high-end trim or light level tuning, setting the maximum light level lower than the true full-on level. Now you're down to about 3 kWh per square foot per year. You do daylight harvesting, taking advantage of the daylight that's coming into the windows and skylights to illuminate the space. Now you're down to less than 2 kilowatt hours a square foot of each year of lighting power. Okay, so you can see that these strategies build on each other, and the more strategies you do in the commercial buildings, the more energy you save. So that was just looking at lighting energy. Here's an example of looking at total building energy, where we have an ASHRAE compliant building on the left, and lighting is the yellow, blue is cooling load, and green is plug loads. You do high-end trim or tuning, you reduce lighting load, you reduce some cooling load. Same thing with occupant sensing. Reduce lighting load, reduce some cooling load. Daylight harvesting, same thing, personal control. So you can save 15-30% total building energy just from lighting control strategies. Okay? Okay, so that gets us to the energy codes. All right, so energy codes understand the importance of lighting and lighting controls, and that's why there's a lot of mandatory provisions in these codes for lighting and lighting controls. All right. So we're going to be talking about ASHRAE 90.1 2016, IECC 2018 and 2015, and California's Title 24. As far as lighting, I don't know if we probably already saw this in the morning session, but just so you know, these codes, they get updated about every 3 years, and every time there's an update, just about, it didn't used to happen in the past, but every time they do a newer version, it's supposed to be more energy efficient than the previous version. Okay, and the goal ultimately is for new buildings to be net zero energy in about 2030. Here's the latest map of code adoption. All right, here we are, Pennsylvania. We're still, so we're going to be going to IECC 2015 for the state and IECC 2018 for Philly. Catch up with our neighbors, all right? So ASHRAE is jointly sponsored. The ASHRAE 90.1 is sponsored by the ASHRAE folks, okay, American Heating, Refrigerating, and Air Conditioning Engineering Society, and IES, Illuminating Engineering Society. So the HVAC gurus and the lighting gurus sponsor that standard, okay? 2016 is the newest version. It's for new construction, additions and alterations of existing buildings. It's for commercial buildings and residential buildings that are 4 stories and higher. An important note here is if you're doing a LEED project, all LEED projects have to meet ASHRAE 90.1 2010 as a minimum. So LEED projects have to go with ASHRAE. And there's interior and exterior lighting requirements and lighting control requirements. IECC is created by the ICC, the International Code Council. 2018 was just published, and it's for new construction, addition, and alterations. They have for all commercial and all residential. There's a whole residential section, even for the low-rise residential. IECC lets you use 90.1 as a compliance path, and there's interior and exterior lighting and lighting control requirements. Okay, and California uses Title 24 Part 6 for their energy code. Do we have people here that work on projects in California? Nobody. Okay, so I'm not going to stay too focused on California. Just note that it's considered the most stringent of all the energy codes, and a lot of provisions actually start there and make their way into ASHRAE and IECC later. So what's different? This is probably the most important slide, because I know you guys want to know, okay, what's changing in the lighting requirements in the new IECC? So I put it in this one table for you, all right? So currently, Pennsylvania's IECC 2009, all right? And we're going to skip IECC 2012 for the lighting part, and go right to 2015. So what changed in 2012 is the following. Lighting power allowances have gotten lower, okay, from the 2009, so you'll see that. And then they added the space-by-space lighting power allowance method. So before, with 2009, there was only a whole building lighting power, watts per square foot of lighting that you can use. Now, if you wanted to get a little bit more lighting power, you can do a space-by-space method and break that building down into individual spaces to basically match what ASHRAE does. They added occupant sensors for certain spaces. Okay, so that doesn't exist in 2009 IECC. OCC sensors have to be set to or programmed to either be, in most cases, either be partial on, so not 100% on, but half on automatically, and then the rest would be manual, or a vacancy sensor, manual on, automatic off. And then functional testing of the lighting controls was added. All right, so that's in 2012 IECC. Now it's all these plus these in 2015. Okay, so even lower lighting power densities or lighting power allowances, the watts per square foot of lighting power that you can use in your spaces and buildings. Automatic daylight responsive control has been added. So in the current energy code, IECC 2009, required just basically for daylight spaces to be manually controlled. Okay, it was really outdated. So now a daylight zone has to be automatically controlled. Okay, and then there are some spaces that require actual continuous daylight dimming. Automatic lighting shut-off for hotel guest rooms was added. Okay, so when the guest room is vacant, lights have to be automatically turned off. Automatic partial off lighting in warehouse open areas and warehouse aisles. Okay, so when the warehouse aisle is vacant, lights have to be reduced by at least 50%. And then they added an additional efficiency option, and one of them is for digital lighting controls. We're going to get into the details on these. Now, IECC 2018 that was just published, which Philly is going to go right to, includes all these and these plus this. So there's even lower lighting power densities. Do we have lighting designers in here? No lighting designers. Okay, well, I'll just say that lighting designers hate the lower lighting power densities, and they keep getting lower and lower, all right? And now it's becoming a problem for a lot of designers. There's an alternate compliance path in the 2018 IECC if you use what they call luminaire level lighting controls. That's where each light fixture has embedded in it occupancy sensing and daylight sensing in each fixture. If you do that for all the lighting on your project, that's a way to comply. Occupancy requirements, partial off occupancy requirements, and regular occupancy requirements were added to Open Office. Okay, a 20-minute timeout. So OCC sensors have to be programmed to 20 minutes or lower, all right? Most manufacturers default to lower than that anyway. And alterations of more than 10% of the luminaires must now comply with the same requirements as if it was new construction, okay? That's what's changed for lighting, all right?
10% is in a building or just a space?
Space. So the way it's supposed to work, and there's a slide on this, but if you change more than 10% of the luminaires in a space, you're supposed to get a permit and meet the same requirements as new construction. Here's a slide that shows the lower lighting power densities of each of these standards. Most of the time, IECC and ASHRAE 90.1 lighting power density, or watts per square foot of lighting power that you can use in your buildings, are the same. And occasionally, IECC and ASHRAE differed. But the point I really want to get across here is these lighting power densities have gotten lower each time they do a new code revision. All right? And up the top table is the whole building method. The bottom is the space-by-space method. That was the lighting requirements, meet those watts per square foot numbers. Now what are the control requirements? There's a requirement for automatic lighting shut-off. Okay, it's in ASHRAE and IECC. The intent here is to eliminate after-hours lighting waste. All right, the requirement is basically that lighting in interior spaces has to be automatically shut off. All right, and you can override that automatic shut-off by up to 2 hours. And the common ways to achieve this are either with a time clock or time switch, or an astronomical time clock or astronomical time switch, or occupancy sensors. It's becoming more common to use occupancy sensors now. Okay, and then they allow a third way, a signal from another control or alarm system that indicates the area is unoccupied. Yes?
Was there still the same exceptions, like the 24/7 space, or where there might be a personal safety factor?
Yes, so there are exceptions that still exist for that. 24/7 is one of them. So I'm giving you like the higher level stuff, but there are going to be some exceptions that affect this. Key notes here, though, that in most spaces, you either have to use partial on sensors, partial automatic on, or vacancy sensors, okay? And then the 20-minute timeout now is in the latest version of these energy codes, okay? Okay, so why do these energy codes require partial automatic on instead of full automatic on, full off, and then even manual on, automatic on? This study shows that manual on sensors, the vacancy sensors, actually save a lot more energy than regular aux sensors. And then the partial automatic on ones even save more energy than the vacancy sensors. Does it sound weird to you guys that partial automatic on actually saves a little bit more energy than manual on, automatic off? Why do you think that is? Someone say it? That's right. So the study basically showed that most occupants were satisfied with the 50% light level, and they didn't turn on the other 50%. So that's why there's additional energy savings there. Okay, so there's also requirements for area control or space control. So every room or every space inside the building has to have a lighting control, okay, to allow occupants to manually turn off the lights. That's the gist of it, okay? So you have to have one control in each room. It has to be readily accessible. You can have it in a remote location as long as there's an indicator that identifies the lights that are being served by the control. Basically, all lighting controls, all manual lighting controls comply with space control. It could be a regular switch, it could be a dimmer, it could be a scene control, it could be a keypad. All right. One important thing, though, is remember the automatic shut-off? You can't override the shut-off by more than 2 hours. So if you're doing a time clock for your shut-off, you got to make sure that the manual controls are connected to that time clock so that if the automatic shut-off sweeps the lights off and an occupant turns the lights back on, that override can't last more than 2 hours. Hotel guest rooms. So this has changed a lot in the latest energy code. So now, in the latest codes, when a guest room is vacant by more than 20 minutes, all the lighting has to be automatically shut off, okay? And that includes the plugged-in lights, okay? So it used to be all you needed was a manual light control at the entrance of the guest room to control only the permanent hardwired lighting in the room, okay? Which usually just, for the standard guest rooms, it's usually just the one light under the door. But now they added all the lights, okay? Captive key card also complies, so that's where you have a slot in your guest room and you put your key in to power the room, all right? I am not a fan of those, because to me, I always get 2 keys when I check into a hotel guest room, and if I have the captive key card, I always have one in that slot. So a better method is truly a method that senses if the guests are in the room or not the captive key card. occupant sensors are required in these spaces. Okay? All right? And in most cases, they have to be partial automatic on or vacancy sensors. Which space on here do you think will allow for a regular full automatic on, automatic off? Yes. So restrooms is one of the exceptions, where you can have just a regular aux sensor that automatically turns the lights full on, automatic off. Okay, so partial automatic off lighting is now required in the latest energy codes. In warehouse spaces, aisles and open areas, lights have to be automatically partial off when those areas are vacant of people, reduced by at least 50%. Okay, that's in all the codes. And then in ASHRAE in California, they added stairwells and corridors, all right, in library stacks. And lastly, in IECC 2018, open offices now have to have occupancy sensor control. Okay, and then when an area defined in the provision is vacant, the lights in that area have to be partially automatic off. Okay, if the whole open office is vacant, then all the lights in the open office go off. Okay, so using occupant sensors with multi-level light fixtures help you meet these kind of requirements. This is, for example, in a stairwell. When the stairwells, by the way, are vacant almost all the time, and the lights are usually just left full on, even though there's nobody there. All right, so this is a big energy saver, where when the stairwell is completely vacant, lights are at a very low level, all right, say 10%, 20%. When the stairwell becomes occupied, the lights go up to a higher level, like 80%. Okay, daylight control is now a key requirement. So before in the old IECC, you just had to do manual. Lights near windows just had to have a separate manual control for those lights. Okay, now they have to be automatically controlled. And you do this with typically with daylight sensors, and dimming ballast, dimming drivers for LED lighting. IECC actually requires continuous daylight dimming now in classrooms, laboratories, libraries, and offices. Okay? It's actually more stringent than ASHRAE, which technically doesn't require continuous daylight dimming. Daylight dimming complies, but you only need like 3 levels to comply. But in those spaces, you have to do continuous daylight dimming. Automatic daylight control, even if it's not dimming, is still required in all the other spaces. Off is now a new step. Okay, so when there's enough daylight in the room, the lights have to be automatically go to off. Okay, and daylight zones daylight zones with 150 watts or less of lighting in the whole space are exempt. All right, a lot of people get this requirement wrong. All right, so if there's multiple daylight zones in a room, okay, you total up the wattage of the lighting in each daylight zone in that room, okay, and if that wattage totals to 150 watts or less, you don't have to do the automatic daylight controls, okay? It's not just the wattage in one daylight zone, it's all the daylight zones for the space, okay? So what is a daylight zone? This is how IECC defines it, and it's similar in ASHRAE and in California. It's one window head height, so that's the top of the window to the floor, one window head height into the space, and then 2 feet on each side of the window, all right? That's the side light daylight zone. And then for skylights, okay, it's basically the area of the skylight, okay, and then 70% of the ceiling height all the way around the skylight. Any electric lights that are in that zone, that's a daylight zone, okay? And if lights are partially in a daylight zone, so just half of the light fixture is in the daylight zone, you still have to control it. Or even if it's just a quarter of the fixture in the daylight zone, you have to control it automatically. Light reduction controls is has been in the energy codes for a while. Basically, the key here is to give occupants an additional light level in addition just to full on and off. Okay? IECC requires a 50% level, so on, full off, and at least 50%. Okay? ASHRAE requires at least a level between 30 and 70%. California Title 24 actually requires, especially if you're doing LED lighting, it requires dimming in nearly every space. Okay, and of course, if you did dimming, that complies. One key exception in IECC is if your space is controlled with an occupant sensor, then you don't have to provide the multi-level lighting. So these are the different ways you can meet that requirement. Basically, you can have the dimming all the lights complies. You can also do what they call dual level switching or bi-level switching, where you switch alternate luminaires off, or alternate rows of luminaires, or alternate lamps in a luminaire off. Preferably, the ideal way to do it is to make sure that if you're doing multi-level lighting, that the illumination is even throughout the space, so you're not going to get like a dark spot and then a light spot, dark spot, light spot. Okay, exterior lighting. Exterior lighting control is a key requirement in all the codes, all right? So this has gotten more stringent in the latest codes. Basically, key requirements are for during daylight hours, exterior lights have to be automatically off. Decorative lighting has to be automatically shut off deeper into the night. And when I say decorative lighting, I'm specifically talking about facade and landscape lighting. So deeper into the night, those have to be automatically off. Okay? And then lighting setback. So lighting, all the other exterior lighting has to be reduced by at least 30% deeper into the night, or when no activity is detected. So that can be time-based or activity-based. All right, and then California actually requires that parking lot lights to be, and ASHRAE, the parking lot lights have to be automatically reduced when no activity is detected. Okay? To comply with these exterior lighting control requirements, time clocks, astronomical time clocks preferably, so you can automatically make sure that during daylight hours, those exterior lights are off, and also using daylight sensors or motion sensors. Motion sensors are basically occupancy sensors for outdoors to meet these requirements. Okay, so now that we have all these mandatory lighting control requirements in the codes, there's now requirements to have them functionally tested to make sure they are installed and going to be used as intended. So IECC and ASHRAE and California Title 24 require that occupant sensors, daylight sensors or photo sensors, time clocks, time switches, and daylight responsive control, demand responsive controls for California be functionally tested. Key thing here, though, is that the person doing the functional testing cannot be part of the design or construction team. Okay, they can be at the same firm, all right, but not necessarily on the same design team for the project. Okay, receptacle control you don't have to worry about for Pennsylvania because it's not in IECC. It keeps failing to make it in the IECC energy code, all right? But just say if you're going to do an ASHRAE project, especially for a LEED project, for example, these spaces, break rooms, open offices, conference rooms, private offices, and classrooms, half of the receptacles in those spaces have to be automatically controlled. Meaning when the space is vacant, those receptacles will shut off the power to anything plugged into those receptacles. Okay? Question?
Would it be like a different color or something? I mean, you go plug your phone in, you walk out of the room and...
Good question. So do they have to be a different color? The requirement in the energy code is they have to be labeled. Mm-hmm. So they have to be somehow marked from the uncontrolled receptacles. Okay? And another key thing here is that you can't use a device that plugs into a receptacle to comply with this provision. It's got to be a permanent part of the building. So those don't count. If you have like a plug-in strip that's plugged into a receptacle that's automatically controlled, that doesn't count. But you can use the same, say, occupancy sensor that's controlling the general lighting in this space to also help control the receptacles. Okay? It doesn't have to be an aux sensor either. It could be a time clock. Yeah, this is probably the least liked code provision. It's very contentious. But again, remember the fastest growing electrical user in commercial buildings is plug loads. All right, so this is at least giving occupants the capability to plug a device into a controlled receptacle if they want to. That's the point of it. Energy monitoring is a requirement in ASHRAE 90.1 and California Title 24, but not in IECC. This is another one that didn't make it into the IECC code, so you don't have to worry about it if you're doing IECC. But basically, whole building electrical energy has to be monitored, and you have to break out HVAC lighting and plug loads separately, okay? And technically the requirement in California is to disaggregate the wiring so you can do monitoring in the future if you want, all right? And it's only for the larger buildings or the large electrical rating buildings. Okay, the idea here is if you're not, to measure it and then make changes if you see issues. That's why this is in energy codes, because they know if you measure it, you're likely to make changes and fix issues and therefore save. Studies show 5 to 15% in energy. Okay, so IECC has a section called optional energy efficiency incentives, all right? And basically all projects have to comply with one of these. One of them is reduced lighting power density. So if you do 10% lower the watts per square foot, you're done. Or they added what they call enhanced digital lighting controls. And what is that? That's basically a lighting system that does this, provides continuous dimming. The fixtures are individually addressable. You can select your specific daylight zones. They're reconfigurable, meaning you can easily, without rewiring, change the light, what controls are controlling a light fixture. So these fixtures are controlled by this sensor, and then later, if the space changes, you can change it to being controlled by another sensor, for example. Load shedding lighting load, especially for demand response purposes, and giving users personal control of the lighting in their individual workspace. So if you have a system that does that, that'll comply with that optional energy efficiency provision. Okay, so we've been talking about the new construction requirements. These are the requirements for existing building alterations as far as lighting. For 90.1 2016, if you replace more than 20% of the lighting load in a space, you have to comply with all the new construction requirements except for daylight responsive controls. Okay? Unless the lighting alteration is what they call a one-for-one alteration. That's where you literally swap one fixture for another fixture. Okay? Or you replace ballasts and drivers and the light source in each fixture, in each existing fixture. If you do that, then you only have to comply with automatic shutoff and the LPD, or lighting power density, watts per square foot. IECC 2018 has gotten even more stringent, and they basically say now 10% of the luminaires in a space, you change 10%. And it's not lighting load, it's number of luminaires. All right, so you do that, you're supposed to meet all the new construction requirements for that space. Okay, so in summary, here's all the new provisions as far as lighting goes in the latest energy codes. Okay, we discussed automatic shut-off, space control, hotel guest room control, aux sensor control, automatic partial off, daylight zone control, light reduction controls, exterior, the functional testing, receptacle control and monitoring, right? And the additional energy efficiency options, and then the alterations requirements. All right, that's a lot, I know. I filled your guys' heads up, so I'm going to summarize it in 3 steps for you, okay? So if you do these 3 things, you should meet nearly all, if not all, your lighting requirements, your lighting control requirements. Give occupants control of their lighting, all right? In addition to just off and on. Give them at least another level. Turn lights off in spaces when they're vacant automatically or when they're scheduled to be vacant, all right? And then lastly, when daylight is available from skylights and windows, use that to illuminate the space, okay? Reduce electric light automatically in the daylight areas. You do these things and you should comply with nearly all, if not all, your control requirements. Okay. So as a real world quick example, we'll look at Glumac Engineering. And they actually renovated a project in Portland, Oregon. All right. Their main goal was to deliver comfort first and then energy savings secondarily too. All right. And in the renovated floor, they put in lighting controls, digitally addressable luminaires, wireless occupancy sensors, wireless daylight sensors, wireless personal dimming. They did the high-end trim and tuning, and they did fully automated shades on the project. Okay. This is the results that they achieved. All right. So this yellow line is the ASHRAE maximum watts per square foot of lighting power that was required in the Oregon code, all right? And that's about 1, all right? But the Oregon code actually was more stringent, which was about 0.9 watts per square foot for the project, okay? They designed the project to about 0.65 watts per square foot of design lighting power, okay? Well below the Oregon code, well below ASHRAE. And here's the actual results where the system is actually operating. This black line, that's the 10th floor, all right? That's not the floor that was renovated. That's just another floor in the building, all right? And you can see throughout the day the lighting power usage. The red line is the floor that was renovated, all right? So they are using about 0.28 watts per square foot of lighting power below their design lighting power because of all the lighting control provisions they put in the building. Okay? That helped them easily meet their energy code and actually helped them also get LEED Platinum for the project. Some key websites for additional information on lighting requirements in your energy codes. In the back of the room, there's some code application guides for lighting requirements for IECC and IECC 2018 and the IECC 2015. And I'll take any questions. Yeah.
Do you know if any of these provisions in your ASHRAE or IECC will require automatic shade controls? Or is it just daylight responsive sensing?
Great question. So are automatic shade controls required in the energy code provisions? The answer is no. So, and by the way, the Glumac project, they use automatic shade control, and that energy savings in that chart, that doesn't even account for the savings from the automatic shade control. That's just from the electric light control. So right now, currently, no. However, in green codes, so you may have heard of green standards like ASHRAE 189.1 or IGCC, there are provisions in those codes that automatic shade control helps meet. And in particular, there's provisions to provide exterior shading or overhangs, okay? So if you don't want to do overhangs, you could provide a fully automatic shade control system or a dynamic glazing system. But that's in the green codes, not in energy codes. Other questions? All right, thank you. And go Eagles!